What if the closest star to our Sun is hiding a world where humans might one day live? In 2016, astronomers discovered Proxima Centauri b, a planet just 4 light-years away. But getting to this distant neighbor isn't just a dream. It's a challenge that modern science is beginning to address. Imagine a journey of more than 25 trillion miles. The technology we have today, such as the ion engines used in deep space missions, pales in comparison to what would be needed for such a journey. But hidden in the blueprints of a decade ago and cutting-edge research are the keys to interstellar travel. But distance isn't the only obstacle we have to overcome. Today, we'll talk about it and find out if humanity's next giant leap can take us to Alpha Centauri. The dream of interstellar travel has been part of the human imagination for centuries. But it wasn't until the 20th century that science began to catch up with science fiction. The journey begins with a momentous moment in 1961, when Yuri Gagarin became the first man to orbit the Earth. This achievement paved the way for space exploration, proving that humans could survive and work beyond our planet. Then came the Apollo program, including the historic 1969 lunar landing. Neil Armstrong and Buzz Aldrin's footsteps on the lunar surface were not only victory for humanity, but also a demonstration of our ability to reach and explore other celestial bodies. In the 1970s, Voyager missions provided invaluable data on the outer planets and heliosphere. These probes, now in interstellar space, carry with them golden records, messages intended for any intelligent extraterrestrial life that might encounter them. The voyages of Voyager 1 and Voyager 2 have given us a glimpse of the vastness of space and the inspiring potential of travel beyond our solar system. But humanity does not stand still. In recent years, the development of advanced propulsion systems has been crucial. Ion engines, used in missions such as NASA's Dawn spacecraft, enable long-duration missions with unprecedented efficiency. These engines use electrically charged particles to generate thrust, a method far more efficient than traditional chemical rockets. At the same time, our understanding of the universe has been revolutionized with the discovery of exoplanets, planets orbiting stars outside our solar system. The first confirmed exoplanet discovery occurred in 1992, when astronomers discovered 2 rocky planets orbiting a pulsar. This discovery shattered previous notions and opened the floodgates to the search for other worlds. In 1995, with the discovery of 51 Pegasi b, the first exoplanet found orbiting a Sun-like star, further reinforced the idea that planets are fairly common in the universe. This gas giant, located about 50 light-years away, ushered in an era of exoplanet discoveries that continues to this day. Among the most exciting discoveries is Proxima Centauri b, discovered only in 2016. This exoplanet orbits Proxima Centauri, the closest star to our Sun, at a distance of only 4.24 light-years. Proxima Centauri b is in the habitable zone of its star, where all the conditions for liquid water to exist could exist. This proximity and potential habitability make this planet a prime target for future exploration, and even potential colonization. The discovery of Proxima Centauri b was made possible thanks to the radial velocity method, which allows you to detect subtle fluctuations in the motion of the star caused by the gravitational pull of the orbiting planet. So far, this method has helped to identify more than 1,000 exoplanets, each of which has become the next step in the search for a world on which life may exist. The feasibility of interstellar travel depends directly on our ability to develop efficient and powerful propulsion systems. Current space travel technology has made significant advances, but it still falls short of what's needed to travel beyond our solar system. Ion engines represent one of the most advanced forms of space propulsion in use today. Unlike traditional chemical rockets, which use explosive reactions to create thrust, ion engines use electricity to ionize the propellant, usually xenon gas. The ionized gas is then accelerated using an electric field, creating sustained and highly efficient thrust. NASA's Dawn spacecraft, launched in 2007, is a prime example of the capabilities of ion propulsion. Dawn's mission was to explore the asteroid belt, in particular the protoplanet Theta and the dwarf planet Ceres. Ion propulsion allowed Dawn to enter and exit orbits around these bodies, which would have been prohibitively expensive with conventional rockets.
Ion engines have a high specific impulse, which means they use fuel much more efficiently than chemical rockets. This efficiency is critical for long-duration missions because it allows spacecraft to take less fuel with them. However, the trade-off is that ion engines require much less thrust than chemical rockets. This makes them unsuitable for launching spacecraft from the Earth's surface, where enormous thrust is needed to overcome gravity. Another milestone in the development of modern propulsion technologies was NASA's New Horizons probe. Launched in 2006, the spacecraft was supposed to explore Pluto and its moons, providing mankind with the first images of this distant world from an incredibly close distance. The probe's journey did not stop at Pluto, but continued on to the Kuiper Belt, a region filled with icy bodies and remnants of the formation of the solar system. New Horizons used a combination of chemical propulsion and gravity assists to achieve its high speed. After launch, the spacecraft received gravitational assistance from Jupiter, which increased its speed and directed it toward Pluto. This maneuver allowed New Horizons to travel more than 3 billion miles in just 9 years, an amazing accomplishment considering such vast distances. While New Horizons demonstrates the height of current space travel capabilities, it also highlights its limitations. Despite speeds of more than 36,000 miles per hour, it took the spacecraft nearly a decade to reach Pluto, and even longer to continue its journey into the Kuiper Belt. For interstellar travel, where distances are measured in light years, we need propulsion systems capable of much higher speeds over long periods of time. Meanwhile, the most intriguing and historically significant advanced propulsion concepts is nuclear pulse propulsion. This technology, conceived during the Cold War era, involves using a series of controlled nuclear explosions to propel a spacecraft. The concept was first proposed by physicist Stanislav Ulam in the 1950s, and later developed into the Orion project. The basic principle of nuclear pulse propulsion is relatively simple. Small nuclear bombs are thrown behind the spacecraft and detonated, and the resulting explosions provide powerful thrust. A large pusher plate attached to the spacecraft absorbs the force of the explosion, propelling the spacecraft forward. The potential of the Orion project was enormous. Calculations showed that such a spacecraft could reach speeds of up to 10% of the speed of light, making it one of the fastest of the proposed propulsion methods. Such a capability would significantly reduce travel time to nearby star systems, including our neighbor Alpha Centauri. Meanwhile, in recent years, the Breakthrough Starshot initiative has become one of the most ambitious attempts to achieve interstellar travel within our lifetime. The goal of this international science project is to send a probe to the Sun, Alpha Centauri, and possibly reach it in just 20 years. Breakthrough Starshot's main innovation is the use of a light sail propelled by an array of powerful ground-based lasers. This light sail, which is a thin and highly reflective sheet, will accelerate to extremely high speeds by transmitting momentum from millions of laser beams. Unlike traditional propulsion methods, this system carries no fuel, making it extremely lightweight and, in theory, capable of speeds up to 20% of the speed of light. Realizing this technology, however, is not without its challenges. The proposed laser array would require a total optical power of about 100 gigawatts, about 100 times the capacity of the world's largest battery. Synchronizing the roughly 100 million lasers to focus their beams on the light sail is a daunting technical hurdle. To solve this problem, researchers from the Australian National University have proposed using a laser guide satellite to help maintain an accurate target throughout the voyage.
Despite such challenges, the potential benefits of this technology are enormous. If successful, the Breakthrough Starshot mission will be able to transmit detailed scientific data and images from Alpha Centauri, providing unprecedented insight into our nearest neighboring star system. While light sails represent a promising near-future technology, other cutting-edge concepts are pushing the boundaries of our understanding of physics. Among them is the theoretical warp drive. Inspired by Einstein's general theory of relativity, a warp engine would manipulate space-time itself, compressing space in front of the spacecraft and expanding it behind, allowing the craft to travel faster than the speed of light without violating the laws of physics.
The concept of warp drive gained attention after the 1994 publication of a paper by physicist Miguel L. Caballeri, who proposed a theoretical basis for such a drive. Although the concept is currently speculative and requires exotic matter with negative energy density, warp drive remains a tantalizing possibility for future interstellar travel. Another innovative concept is the Freeman-Dyson interstellar jet engine. This hypothetical propulsion system would harness the energy of a star, using a series of mirrors or lenses to focus stellar energy onto a spacecraft. The collected energy would then be converted into thrust, propelling the spacecraft at high speeds. While Dyson's concept is intriguing, its practical realization faces serious obstacles. Capturing and converting enough stellar energy to achieve meaningful thrust would require materials and engineering capabilities many times greater than our current technology. Perhaps the most powerful of the proposed propulsion systems is a propulsion system based on antimatter. Antimatter, coming into contact with matter, annihilates both particles, releasing huge amounts of energy. A spaceship powered by antimatter can theoretically reach speeds approaching a significant fraction of the speed of light. The potential of antimatter propulsion is staggering, but so are the challenges. Antimatter production is currently a highly inefficient and expensive process, and its safe storage represents additional challenges due to its highly reactive nature. Despite these obstacles, antimatter research continues, as it promises to be an unprecedentedly efficient engine. Huge distances present the most obvious obstacle. Nevertheless, even with a modestly efficient propulsion system, only a fraction of the difficulties would be overcome. Interstellar travel is an enormous undertaking, fraught with technical and logistical challenges. Even with the most advanced propulsion systems, traveling to our nearest star system, Alpha Centauri, requires overcoming enormous technical obstacles. One of the main technical problems is protection against radiation. Space is filled with high-energy particles from the Sun and distant space sources. Prolonged exposure to this radiation can be deadly to both humans and sensitive electronic equipment. Modern spacecraft use a combination of physical and electronic shielding to protect against radiation, but these methods are insufficient for the prolonged exposure expected during interstellar travel. Advanced materials and innovative shielding techniques are being explored. These include the use of magnetic fields to deflect charged particles, and the development of new composite materials that provide better protection without excessive weight gain. However, creating effective and lightweight radiation shielding remains a major challenge. Another technical hurdle is maintaining the structural integrity of the spacecraft themselves over the long term. Spacecraft designed for interstellar travel must be able to withstand the stresses associated with launch, long stays in space, and possibly collisions with micrometeoroids and other space debris. The high speeds required for interstellar travel exacerbate these risks, since at such speeds, even tiny particles can cause significant damage. Engineers are exploring advanced materials such as carbon composites and reinforced alloys to improve spacecraft durability. In addition, modular designs that allow for in-flight repair and maintenance could be critical for long-duration missions. The vast expanse of space presents another logistical challenge.
Even at a significant fraction of the speed of light, it would take decades to reach the nearest star systems. Advances in autonomous systems and long-term life support are needed to keep a spacecraft operating reliably for such a long time. Solutions such as hibernation or suspended animation are already being explored, but these technologies are still in the experimental stage. In addition to technical and logistical challenges, interstellar travel faces serious economic and political obstacles. The cost of developing, building, and launching an interstellar mission is astronomical, no pun intended. Governments, private enterprises, and international consortia will have to collaborate and pool resources. Historically, space exploration has been funded primarily by national governments, but the growing involvement of private companies such as SpaceX and Blue Origin suggests a potential shift to more diverse funding models. The search for habitable planets, especially in the Alpha Centauri system, is one of the key areas of modern astronomy.
As you may have already realized, the discovery of Proxima Centauri b in 2016 was an important milestone that showed the possibility of habitable worlds in our nearest neighboring star system. This exoplanet has sparked numerous missions and research initiatives aimed at figuring out its characteristics and potential to support life. To continue this research, the European Southern Observatory has developed a new instrument designed specifically to search for exoplanets in the Alpha Centauri system. This advanced instrument, part of the Very Large Telescope in Chile, enhances our ability to detect Earth-like planets by improving the accuracy of radial velocity measurements. The instrument aims to identify Earth-sized planets by detecting the tiny gravitational fluctuations they cause in their host stars. Focusing on Alpha Centauri A and B, the two Sun-like stars in the system, this instrument seeks to detect additional planets that may lie within their habitable zones. The improved sensitivity and resolution of this technology promises to reveal planets that have not previously been detected, giving a clearer picture of the potential for habitable worlds in our nearest star system. The importance of discovering a habitable planet in the Alpha Centauri system cannot be overemphasized. Such a discovery would be a tremendous step forward in our quest to understand how widespread habitable conditions are beyond our solar system. A habitable planet in such close proximity would be a prime candidate for future interstellar missions and a potential target for human colonization. Recent discoveries in the search for habitable exoplanets have been promising. For example, late this spring, astronomers discovered the Earth-like exoplanet Gliese 12b, located just 40 light-years away. This planet, comparable in size to Venus, orbits a red dwarf star and is estimated by scientists to have a surface temperature of about 107 degrees Fahrenheit. The discovery of such a planet, which may have an atmosphere, provides insight into the conditions necessary for a planet to retain an atmosphere and for liquid water to exist. The discovery was made possible by NASA's Transiting Exoplanet Survey satellite, which detects exoplanets by observing a small, dimmer star as the planet passes in front of it. During such transits, the star's light passes through the exoplanet's atmosphere, allowing astronomers to analyze its composition using transmission spectroscopy. The significance of Gliese 12b goes beyond its potential habitability. It serves as a valuable point of comparison for understanding why Earth and Venus, despite their similarities, have very different environments. By studying Gliese 12b, scientists hope to learn more about the atmospheric retention and evolutionary pathways of Earth-like planets orbiting cold stars, which are the most common type of stars in the Milky Way. Gliese 12b's estimated size may be as large as Earth, or slightly smaller, comparable to Venus in our solar system. Current efforts to find and study potentially habitable planets around Alpha Centauri and other nearby stars continue to evolve. Instruments such as JWST are expected to play a crucial role in this search, providing a deeper understanding of the conditions that could make these planets habitable. On the other hand, no one is saying that humans should be the first to explore these distant worlds.
Even without the advanced technology necessary for human survival, we can still send probes to pave the way. Intelligent robotic probes and artificial intelligence have a key role to play in the future exploration of interstellar space. These technologies can operate autonomously, handling complex tasks without direct human intervention, making them ideal for long-duration missions far beyond our solar system. One of the most intriguing concepts in this regard is the so-called von Neumann probes. These theoretical, self-replicating machines could explore the galaxy using local materials to create their replicas, exponentially increasing the number of probes with each replication. This approach could provide extensive exploration and potential colonization without requiring constant resupply from Earth. However, when it comes down to human space exploration, the idea of interstellar arcs and self-sustaining habitats represents a visionary approach to colonizing distant star systems. These massive spacecraft would host large communities, providing everything needed to sustain life during multi-generational journeys to other stars. These habitats will be equipped with advanced life support systems, agricultural facilities, and social infrastructure to ensure the well-being of their inhabitants.
In conclusion, while our current technology limits us to relatively modest space travel, these advanced concepts offer a glimpse into a future in which we can transcend the space barriers that confine us to our solar system. As technology advances, these concepts may well move from science fiction to reality, paving humanity's path to the stars. Are we alone? This question is, in some ways, as old as the starlight that travels through the eons to reach us. Since the earliest civilizations, our ancestors have looked up at the night sky in wonder, their imaginations fired by the flickering lights overhead. Today, armed with the power of modern science and technology, we still await the answer to this age-old question. But our goal is not just to find primitive life, but to discover the whispers of civilizations that might share this grand cosmic stage with us. The Breakthrough Listen project, the most ambitious search for these whispers' techno-signatures, is pushing the limits of our hearing in an attempt to capture the murmurs of extraterrestrial life. As we stand at this crossroads of discovery, several teams of scientists in the Breakthrough Listen study and other SETI projects have already published several scientific papers, moving us closer to answering this question. So, how close are we to the goal in this grand quest? What non-trivial decisions have been made to ensure a seamless search for signals and improve our chances? Let's get to the bottom of it. In our celestial odyssey to unlock the mysteries of life beyond Earth, scientists have charted two major paths across the cosmic seas: the search for biosignatures and the search for technosignatures. Each path offers a unique lens through which to view the potential for life in the universe, guided by the principles of astrobiology and the advanced technologies at our disposal. Biosignatures, the chemical fingerprints of life, serve as beacons in our search for biological activity on distant worlds. These signatures are not just markers, but signs of complex interactions between living organisms and the environment. Every molecule, from the oxygen and ozone created by photosynthetic life forms to the methane and carbon dioxide produced by biological and geological processes, carries a story of potential life. The James Webb Space Telescope, JWST, with its unprecedented sensitivity to the infrared spectrum, is our most advanced scout in this endeavor. Using transmission spectroscopy, JWST can analyze, dissect light from distant stars as it passes through the atmospheres of orbiting exoplanets. This light bears the fingerprints of various molecules, each absorbing certain wavelengths and leaving behind a spectral signature that JWST can detect and analyze. Peering into the depths of space, JWST searches out these spectral lines with precision, allowing us to infer the presence of water vapor, carbon dioxide, methane, and other potential biosignatures in the atmospheres of exoplanets. This method not only hints at the possibility of life, but also provides insight into the atmospheric composition, climate, and habitability of these distant worlds. Parallel to the search for biosignatures is the search for technosignatures, the hallmarks of advanced technological civilizations. Unlike biosignatures, which indicate the presence of life in any form, technosignatures suggest a leap to complexity, where life has evolved to use and manipulate its environment in profound ways. From radio signals to megastructures orbiting distant stars, technosignatures embody the potential to detect not only life, but also societies that may have mastered the art of cosmic communication. The pursuit of technosignatures spans the galaxy. Initiatives like the Breakthrough Listen project utilize vast networks of radio telescopes to listen to and eavesdrop through space. These telescopes scan the sky for narrowband radio signals, anomalies in the natural cosmic radiophone that may indicate deliberate transmissions from intelligent beings. Biosignatures are whispers of life embedded in the fabric of a planet's atmosphere, providing a glimpse into invisible worlds orbiting distant stars. Among the vast number of potential biosignatures, 4 stand out for their significance: oxygen and ozone, phosphine and ammonia, methane and carbon dioxide, and mysterious, unexpected combinations of molecules. Oxygen, the breath of life on our planet, and its companion, ozone, form the first pair of key biosignatures. On Earth, oxygen is a byproduct of photosynthesis, the process that formed our atmosphere and allowed life to thrive. The presence of ozone, a molecule formed from oxygen by the sun's ultraviolet radiation, provides a protective layer, shielding the surface from harmful radiation.
The discovery of these molecules in the atmosphere of an exoplanet could indicate the presence of a thriving biosphere, perhaps similar to our own. Phosphine and ammonia, less common but no less intriguing, represent a second pair of biosignatures. Phosphine, a gas associated with anaerobic ecosystems on Earth, has been proposed as a potential marker of biological activity on other planets. Ammonia, another molecule with biological ties, may indicate the presence of life, especially in environments where it's not expected to exist in significant quantities due to non-biological processes.
Methane and carbon dioxide form the third cornerstone of our quartet of biosignatures. Methane, a potent greenhouse gas, can be produced both biologically, by organisms such as methanogens, and abiotically, by geologic processes. Carbon dioxide, a critical component of Earth's carbon cycle, is a product of respiration and volcanic activity. The simultaneous presence of methane and carbon dioxide, especially in unexpected ratios, may hint at biological processes in nature. Finally, with the fourth point, we move into the realm of unexpected combinations of molecules, methane and carbon dioxide, which cannot be stably present in more or less large quantities simultaneously without being transformed into other substances. Such combinations defy conventional expectations and point to the possibility of life functioning based on alien biochemical processes. The James Webb Space Telescope, JWST, humanity's most advanced observatory, is designed to study the atmospheres of exoplanets in search of these very biosignatures. Using transmission spectroscopy, JWST studies light from a star as it passes through a planet's atmosphere during its transit. When light passes through atmospheric gases, certain wavelengths are absorbed by the molecules, leaving behind a spectral fingerprint that JWST can detect and analyze. On the other hand, technosignatures, like the fingerprints of advanced civilizations, offer a different path in our quest to discover not just life, but societies that have reached a level of technological sophistication, perhaps similar to or even superior to our own. Unlike biosignatures, which hint at the mere presence of life,
Technosignatures speak of the ability of civilizations to alter the environment on a grand scale, communicate across the stars, and harness energy in ways we're only beginning to imagine. Technosignatures cover a wide range of signals and structures, from radio waves unintentionally emitted by a planet's communication networks to deliberate beacons aimed at the stars, from colossal energy collectors known as Dyson spheres to the barely perceptible glow of city lights on the exoplanet's night side. These signatures, if detected, will not only indicate the presence of life, but will also provide deep insights into the technological capabilities of alien civilizations. Our own planet is a prime example of a world teeming with technosignatures. Every radio broadcast, every satellite, and every piece of space debris orbiting the Earth creates a symphony of signals that, to the distant observer, unmistakably indicate the presence of an advanced civilization. The very fabric of our daily lives, from global communications networks to space probes venturing into the unknown, generates a cascade of signals that radiate out into space, making our presence known to all who can hear us. But why are technosignatures a more accurate way to search for technologically advanced civilizations? The answer lies in their specificity and the intentional or significant nature of the signals and structures they represent. While biosignatures can occur from simple microbial life to complex ecosystems, technosignatures clearly indicate a level of technological development and intent. The discovery of a technosignature not only confirms the existence of life, but also indicates that this life has crossed the threshold of cognitive and technological capability, engaging in activities that leave an indelible mark on the cosmic canvas. Breakthrough Listen was launched in 2016 with an ambitious mission to scour the cosmos for signs of technologically advanced civilizations. The project represents one of the most comprehensive searches for alien technosignatures ever undertaken. Armed with state-of-the-art technology and unprecedented scope, the project utilizes some of the most powerful radio telescopes in the world, including the Green Bank Telescope and Parkes Observatory. These colossal ears, tuned to the quiet whispers of the universe, can detect a range of signals, from faint radio emissions from distant stars to potential transmissions of extraterrestrial origin. At the heart of the mission is the desire to detect technosignatures, signals that, by their nature, can only be produced by technological means. These can range from narrowband radio signals that differ from the natural background noise of space to powerful laser pulses that cut through cosmic clutter. The project had previously focused on the Milky Way galaxy for strategic reasons. To begin the search in our cosmic neighborhood, where such signals may be strongest and most detectable, the Milky Way, with its billions of stars, provides fertile ground for such work.
Each observable star is a potential sun for other planets. Each planet a potential cradle for life as we know it, or life yet to be imagined. The project was originally designed not just to search for signals in our galaxy, but to explore in depth the nature of life and intelligence in the universe. Sifting through the cosmic expanse of the Milky Way, looking for signs of life, is akin to searching for a single word spoken in a whisper in the middle of a bustling metropolis. A galaxy of about 100 billion stars can easily conceal the signals of other civilizations. The task of monitoring such a vast array of targets for technosignatures is monumental, not only because of the large number of stars, but also because of the complex array of cosmic phenomena that can obscure or mimic the signals we are looking for. The problem is compounded by the limitations of our current technology and the limited resources at our disposal. Even with the most advanced radio telescopes, we can only listen to a small fraction of the stars in the galaxy at any given time. Huge distances dilute the signals, making them fainter as light years pass.
and various natural cosmic phenomena, such as the emission from pulsars and nebulae, add further complexity to the search. In the face of these challenges, astronomers and scientists have looked beyond the familiar boundaries of the Milky Way to the wider universe. By observing galaxies as individual entities, each made up of billions of stars, we can try to pick up the cumulative signals of advanced civilizations. This extragalactic strategy is based on the premise that a sufficiently advanced civilization can harness technologies that affect its entire galaxy, from building megastructures like Dyson spheres to harnessing the energy of supermassive black holes. Such grandiose endeavors could lead to technosignatures that, in theory, could be found in vast intergalactic voids. The transition to extragalactic studies comes with some challenges, from even greater distances to the need for more sensitive instruments and more sophisticated methods of data analysis. Nevertheless, each galaxy observed and each dataset analyzed brings us closer to understanding whether we're truly alone in the universe or part of a grander galactic world. Extragalactic exploration is exactly what Carmen Choza and her team did in 2023. Using the Robert C. Byrd Green Bank Telescope, the team has embarked on an ambitious mission to observe the centers of 97 nearby galaxies, studying them for 5 years. This work, one of the largest of its kind, used a search for narrowband Doppler drift in 4 frequency bands from 1 to 11 gigahertz. The goal was to detect signals that could come from civilizations capable of using energy equivalent to that of a Kardashev Type II civilization. The most important aspect of this study was the implementation of the TurboSETI pipeline, a sophisticated tool designed to search for Doppler drift. This pipeline played a crucial role in analyzing the vast amount of data collected during the study, to combat the persistent problem of radio frequency interference, called RFI, which often mimics extraterrestrial signals. The team adopted an on-source, off-source cadence pattern. This method involves alternating between observations of a target galaxy, on-source, and a nearby region devoid of the target, off-source, and is repeated 3 times for each galaxy. Because RFI interference and localized noise are present regardless of the telescope's pointing, they'll appear in both on-source and off-source observations. In contrast, a true astronomical signal should only manifest itself in observations from the source, and not in the observations beyond the source. This approach helped to distinguish real astronomical signals from terrestrial interference, which improved the reliability of the results. Despite careful methodology and advanced technology, the study faced significant challenges, primarily due to radio frequency interference. The team's innovative radio interference mitigation strategies, including signal injection and recovery tests, were crucial in differentiating terrestrial and potential extraterrestrial signals. These efforts emphasized the difficulty of finding technosignatures, especially since signals must be significantly more powerful than those detectable within our galaxy to be considered extragalactic. The exhaustive search resulted in 6,034,313 hits across all observed galaxies.
These matches represent cases where the data analysis pipeline has identified signals that potentially stand out from the background noise and may be of interest for further study. From the original 6,034,313 matches, further refinement and analysis using a computer algorithm narrowed the field to 1,519 events of particular interest. These events were then scrutinized by the research team, which attempted to distinguish potential extraterrestrial signals from the all-pervasive RFI noise. Despite the complexity, the team eventually concluded that all 1,519 events were associated with terrestrial sources, or natural cosmic phenomena. However, the work done by Choza and her team not only illuminates the path we've traveled, but also beckons us to new horizons. The ability to reanalyze data through the subtle prism of machine learning
promises us a chance to uncover signals that previously remained obscure or were perceived as noise. This changing landscape of SETI research, constantly enriched by technological innovation, invites us to look deeper. As we move forward, armed with improved tools and a deeper understanding of the challenges that await us, the search for extraterrestrial technosignatures continues. In the meantime, we'll be eagerly awaiting new opportunities to solve the mysteries of the cosmos. In the vastness of our solar system, beyond the belt of asteroids and gas giants, lies a world shrouded in mystery. Neptune, the eighth planet from our Sun, a distant ice giant, has long captured our imagination. For decades, we've imagined it as a dark blue sphere at the edge of our cosmic neighborhood. But what if the vision of this distant world was an elaborate illusion? This mysterious planet, named after the Roman god of the sea, has hidden its true colors from us. Cloaked in a shroud of deep blue, Neptune has been the subject of many stories and scientific investigations. But recent discoveries have removed this azure facade, revealing a reality far more complex and fascinating than we could have imagined. For years, our telescopes have been pointed at this distant giant, capturing its essence in pixels and data. What we saw, however, was not the reality of the planet, but a reflection of our own technological and perceptual limitations. The deep blue color we associated with Neptune was actually the result of our own interpretations and enhancements, a story we unwittingly created and believed. Today, we invite you to explore Neptune like never before. Delve into its true colors, understand its dynamic atmosphere, and unravel the secrets of its moons and rings. For centuries, Neptune was portrayed as a dark blue world, whose color reflected its cold, distant nature in the solar system. This representation, deeply ingrained in our collective consciousness, has become the cornerstone of our understanding of this icy giant. But what if this image was a reflection of our perceptions, rather than the planet's true appearance? Neptune's color is a story of scientific evolution and the search for truth. It begins with a Voyager 2 probe launched by NASA in 1977. Sent to the outer reaches of the solar system, it took the first close-up images of Neptune, painting a picture of the planet awash in a stunning blue color. However, these images were not a direct window into the true color of Neptune. In fact, they were interpretations, the result of processing the data through the lens of human understanding and the technological capabilities of the time. The deep blue color we saw was the product of enhancements made by scientists to emphasize certain features of the planet. This story began to unravel with the advent of more advanced telescopes, such as the Hubble Space Telescope and the Very Large Telescope. These instruments, equipped with state-of-the-art technology, allowed astronomers to see the true color of the planet again. The results of this study were striking. The new images revealed that Neptune's color was not the previous deep blue, but rather a more muted and varied shade. This discovery was not just aesthetic, but a fundamental shift in our understanding of the planet. The reason for this color misconception lies in the way we process and interpret astronomical data. Colors in space images are often enhanced or altered to emphasize certain features, or to make them more distinguishable to the human eye. In the case of Neptune, these enhancements over time have led to a collective opinion of its deep blue color. So, what led to this discovery? The key lies in a meticulous study entitled Modeling the Seasonal Cycle of Uranus's Color and Magnitude and Comparison with Neptune. This study, led by Patrick G.J. Irwin of Oxford University, along with a team of experts, set out to unravel the mysteries of Uranus's seasonal color changes. However, their journey will inadvertently shed light on the true colors of Neptune, disproving long-held beliefs.
The team carefully analyzed a huge array of data obtained from Lowell Observatory over 6 decades. These data, supplemented by Hubble Space Telescope observations, produced a detailed picture of Uranus's disk-averaged color and photometric magnitude, revealing the complex interplay of its seasonal changes. One of the most important aspects of this study was the focus on the reflectivity of Uranus and the abundance of methane. The researchers unraveled a complex relationship between the lower methane content at polar latitudes and the different reflectivity of aerosol particles. This complex interaction of elements in the atmosphere of Uranus was thought to be influenced by the presence of methane ice particles, adding a new layer of complexity to our understanding. In parallel, the study allowed for a fascinating comparison with Neptune. Contrary to popular belief, the difference in blue hues between Neptune and Uranus was less pronounced. This discovery was the result of a critical reassessment of Neptune's color, disproving the image of deep blue that had been ingrained in our minds. The methodology used by the team was a combination of quantitative analysis, atmospheric modeling, and advanced spectroscopic observations. They converted measured reflectance spectra into radiance spectra, and then into tristimulus values. This process mimicked the visible colors of the planets as perceived by the human eye, bridging the gap between the raw data and our visual interpretation. The use of advanced telescopes, such as Hubble and the Very Large Telescope, played an important role in this endeavor. These technological marvels allowed the team to revisit and re-examine the true colors of Uranus, and by extension Neptune, with unprecedented accuracy. As we delve deeper into the mysteries of Neptune, we find ourselves amid a maelstrom of atmospheric activity. In stark contrast to the relative calm of its stellar neighbor Uranus, Neptune's atmosphere, a turbulent and dynamic formation, is home to some of the most extreme weather in our solar system. One of the most striking features of Neptune's atmosphere is the presence of colossal storms, the most famous of which is the Big Dark Spot. Discovered by the Voyager 2 spacecraft in 1989, this massive storm, similar to Jupiter's Great Red Spot, is a testament to the turbulent nature of the planet. A large, dark spot, a giant, rotating storm, is a window into Neptune's intense atmospheric dynamics. These storms are caused by the strongest winds in the solar system, reaching speeds of up to 1,300 miles per hour. However, to this day, the power and magnitude of these winds are a mystery to scientists, raising questions about their origin and the energy sources that drive them. In contrast, neighboring Uranus is a picture of tranquility. Its atmosphere, although composed of hydrogen, helium, and methane, does not have the same violent storms and extreme winds as Neptune. The difference in atmospheric activity between these two ice giants is one of the many mysteries of our solar system. Another intriguing aspect of Neptune's atmosphere is the presence of unusual hotspots, where temperatures can reach a staggering 750 degrees Kelvin. These hotspots represent a paradox because they exist on a planet so far from the Sun. The source of this heat remains a mystery, but theories suggest it could be caused by internal processes, such as auroras or magnetic reconnection in the plasma layers. The origin of these hotspots and the extreme weather conditions on Neptune are the subject of ongoing research. They force us to seek new answers to questions about planetary atmospheres and hint at complex internal processes that have yet to be understood. Stepping outside Neptune's turbulent atmosphere, we enter a realm of celestial harmony, where moons and rings swirl around this icy giant. Turning our gaze to Triton, Neptune's largest and most intriguing moon, we discover a world of seasonal changes and atmospheric mysteries. Triton, a unique moon with a retrograde orbit, was the last solid object visited by the Voyager 2 spacecraft during its historic journey through the outer solar system. Because of its retrograde orbit, indicating that it was captured by Neptune's gravity, Triton stands out among the moons of our solar system. Its surface, covered in nitrogen ice,
is geologically young and active, with dark green streaks indicating the presence of geysers spewing nitrogen gas. Triton's thin atmosphere, whose thickness varies with the seasons, is a fascinating study in extraterrestrial meteorology. Observations with the European Southern Observatory's Very Large Telescope have revealed that Triton's southern hemisphere is in the height of summer. This distant moon, despite its relative distance from the Sun, is experiencing significant atmospheric changes.
The heat of the summer sun causes the thin layer of frozen nitrogen, methane, and carbon monoxide on Triton's surface to sublimate into gas. This process causes the icy atmosphere to thicken as the season continues in Neptune's 165 Earth-year orbit around the Sun. The season on Triton lasted more than 40 years, and the southern summer solstice occurred in 2000. The discovery of carbon monoxide in Triton's atmosphere, as well as the confirmation of the presence of methane, marked a significant advance in our understanding of this moon. The presence of these gases, especially the enrichment of ice with carbon monoxide in the upper surface layer, feeds the atmosphere and determines its seasonal dynamics. These findings required a revision of Triton's climate and atmospheric models. The complex interaction of nitrogen, methane, and carbon monoxide not only determines atmospheric conditions, but also provides insight into the geologic and climatic history of the moon. But Triton is not alone. The planet is accompanied by a retinue of smaller moons, each contributing to our understanding of this distant world. These moons also show seasonal changes and provide insight into the complex gravitational interactions and environmental conditions around Neptune. When we turn our gaze from the moons to Neptune's rings, we encounter another aspect of this planet's mysterious nature. Neptune's rings, made up of a mixture of dust and ice particles, are dull yet mesmerizing. They testify to the planet's dynamic history. Scientists believe they're remnants of moons that were destroyed by collisions were torn apart by Neptune's gravity. The composition and characteristics of these rings are closely related to Neptune's true color and atmospheric phenomena. The subtle hue of the rings, which, reflected by light scattering in Neptune's atmosphere, add another layer to the planet's color palette. The rings, reflecting and refracting light from the Sun, create the overall appearance of Neptune, seen from afar. In 2022, the James Webb Telescope captured the clearest view of the rings of this distant planet in 30 years. Photographed with unprecedented clarity, these rings have changed the way we think about this distant planet. The most striking thing about the new Webb image is the clear view of Neptune's rings. Some of these rings, dim and dusty, have not been detected since the historic Voyager 2 flyby in 1989. The Webb telescope, with its enhanced capabilities, has brought these elusive rings back into focus. Neptune's rings are made up of several bright and narrow, as well as fainter dust bands. Infrared imaging by the Webb telescope has put these rings in a new light, revealing features that were previously hidden in the darkness of space. This is the first time these rings have been seen in the infrared spectrum, providing new insights into their composition and behavior. Neptune's rings, like the planet itself, are characterized by a unique composition. Unlike the gas giants Jupiter and Saturn, Neptune is an ice giant, rich in elements heavier than hydrogen and helium. This composition also reflected in the planet's signature blue color invisible wavelengths, caused by a small amount of methane gas. In infrared images taken by Webb's NIRCam near-infrared camera, Neptune does not appear blue. In contrast to the darkened appearance one would expect due to methane absorption of light, in infrared images taken by the Space Telescope, Neptune appears as a luminous, glowing white sphere. This absorption also affects the appearance of Neptune's rings,
as they reflect and refract light traveling through the planet's atmosphere. This unexpected brightness in the infrared is the result of a unique interaction between the planet's atmosphere and infrared light. While methane gas absorbs red and infrared light, high-altitude clouds in Neptune's atmosphere reflect sunlight before it's absorbed. These methane ice clouds appear as bright streaks and spots that cast a ghostly glow on the planet in the infrared spectrum. By the way, you may wonder why Triton looks like a dazzling point of light, adorned with shining spikes, as opposed to the more subdued image of Neptune. These diffraction spike patterns are a characteristic feature of the imaging telescope. They're not physical structures, but rather optical artifacts created by the telescope's design. Light from Triton passing through the mirrors and telescope structure is diffracted, resulting in these striking peaks emitted by the Moon. Diffraction, in simple terms, is what happens when a wave, such as light, travels around the edge of an object or through a small opening.
In the context of the James Webb Space Telescope and its images, diffraction peaks arise because of the way the mirrors and structure of the telescope are arranged. When light from a bright object, such as a star or Triton in images of Neptune, enters the telescope, it's bent slightly by the edges of the mirrors and other parts of the telescope. As a result of this bending, the light diverges and forms the star-like spikes we see in the images. The study of Neptune's rings, especially in the infrared, provides valuable insights into the atmospheric conditions and internal composition of the planet. The interaction of the rings with Neptune's atmosphere, particularly the methane ice clouds, provides insights into the planet's climactic and environmental processes. The bright equatorial band that girdles the planet hints at the global atmospheric circulation, a key driver of the planet's winds and storms. The atmosphere, which sinks and warms near the equator, glows more intensely in the infrared than the cooler gases that surround it. As we conclude our journey through the mysterious world of Neptune, we reflect on the impact these discoveries are having on the broader field of planetary science and exoplanet exploration. Neptune, once a distant blue spot, is now a testament to space exploration's dynamic and ever-evolving nature. Discoveries concerning Neptune's true color, its atmospheric phenomena, and the intricate details of its rings and moons go far beyond our solar system. They provide a crucial example for understanding similar ice giants and exoplanets in the far reaches of our galaxy. The insights gained from Neptune will help astronomers decipher the mysteries of these distant worlds and enrich our knowledge of the universe. As we continue to gaze into the cosmos, Neptune reminds us of the limitless potential for discovery. Its example encourages us to keep looking, asking questions, and unraveling the mysteries of the universe. The Moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folkloric tales, the Moon holds secrets that have eluded us for centuries. Among these mysterious features is the Moon's South Pole, a region shrouded in perpetual shadow and intense cold, untouched and unexplored by any previous lunar mission. This is the story of Chandrayaan III, India's daring journey into uncharted territory. Launched on a journey of more than 238,600 miles, Chandrayaan III embarked on a mission not just of distance, but of discovery. Its purpose? To unravel the mysteries of the Moon's South Pole, a place where sunlight barely reaches, an area where the terrain is so treacherous that you have to wade through an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan III sought answers to questions that have puzzled scientists for decades. What lies beneath the surface of this mysterious region?
Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here in the form of ice. When Chandrayaan III ventured beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. Its primary goal was clear, yet challenging: to achieve a soft landing near the Moon's south pole, a feat that had never before been accomplished. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists and engineers piloted this ambitious mission. Their expertise helped Chandrayaan III traverse the space void, overcoming the challenges of lunar orbit insertion and descent. The south pole of the Moon is a landscape unlike any other. Here, the terrain is a patchwork of craters and mountains, many of which are shrouded in perpetual darkness. The challenge was not just to land, but to land safely, in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram landing module separated from the orbiter, it began its descent. The landing module, equipped with advanced sensors and engines, began its perilous journey to the surface of the Moon. Imagine a spaceship autonomously navigating a maze of craters and boulders in search of a patch of land safe enough to land on. The landing module's onboard systems were hard at work, analyzing every inch of the terrain below. Against this treacherous landscape, the landing module also struggled with extreme temperatures. The Moon's south pole is a place of stark contrasts. The sun barely rises above the horizon, while shadows hide frigid temperatures that can drop to -382 degrees Fahrenheit. As the landing module made its final approach, the hearts of the Flight Control Center beat harder. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a light thud, Vikram landed,
marking an historic moment not only for India, but for lunar exploration in general. In the silence of the Moon's south pole, Chandrayaan III began its mission of exploration and discovery. So, after the historic landing of Chandrayaan III, a new chapter in lunar exploration began. The mission's goal was to maximize the study of the Moon's characteristics, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just beneath its surface. The lunar exosphere, the thin layer of gases surrounding the Moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, the Moon's exosphere is so rarefied that it almost resembles a vacuum. The Chandrayaan III instruments, developed using the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delved deeper into the Moon's ionosphere. This layer, formed by solar energy ionizing atoms in the exosphere, plays a crucial role concerning lunar communication and navigation. The Chandrayaan III measurements were designed to provide unprecedented information on the density and behavior of the ionosphere, which is important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was studying the temperature variations just beneath the lunar surface, using one of 4 instruments on the landing module, CHASTE, or Chandra's Surface Thermophysical Experiment. The temperature probe, immersed in the lunar regolith, was tasked with the critical mission of mapping the thermal profile of the lunar soil. The results of Chandrayaan III revealed a sharp contrast in temperatures. On the surface, during a lunar day, temperatures rose dramatically to 140 degrees Fahrenheit, while just 8 centimeters deeper, they dropped significantly to 14 degrees Fahrenheit, demonstrating the lunar soil as a potential thermal insulator. This discovery provided new opportunities for future lunar habitats, suggesting that the lunar regolith could serve as a thermal insulator, protecting astronauts from the Moon's harsh, extreme temperatures and harmful radiation.
These studies were more than just scientific endeavors. They were stepping stones toward a future in which the Moon could be a gateway to future space exploration. Mission results on the lunar exosphere, ionosphere, and subsurface temperature laid the foundation for understanding the Moon's environment and its potential to support human life. Standing in the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon that had not been observed for more than 50 years: a lunar earthquake. The mission succeeded in shedding light on one of the most intriguing and least understood aspects of the Moon. The Instrument for Lunar Seismic Activity, or ILSA, a seismic instrument, was designed to detect the slightest tremors on the Moon. And it did. Chandrayaan-3 detected what looked like a lunar earthquake, a significant discovery, given that the last such observation was made during the Apollo missions in the early 1970s. Lunar quakes are fundamentally different from earthquakes. While Earth's seismic activity is largely due to the movement of tectonic plates, the Moon, which is devoid of these plates, experiences earthquakes for a variety of reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a subject of scientific interest. The Chandrayaan-3 data suggests several possible causes for these earthquakes. One theory is a collision with meteoroids, which could cause shock waves that penetrate the Moon's crust. Another is Earth's gravitational pull, causing tidal forces that load the lunar crust. And finally, extreme temperature fluctuations on the Moon's surface can cause expansion and contraction, leading to earthquakes. These earthquakes are not just surface phenomena, they're windows into the Moon's interior. By analyzing the seismic waves, scientists can infer the composition and structure of our satellite's interior, which resembles a sonogram of the lunar interior. Such information is of great importance for understanding the formation and evolution of the Moon. The detection of a lunar earthquake by the Chandrayaan-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened up new insights into the geological processes that shape the Moon. To unravel the geologic mysteries of the Moon, Chandrayaan-3 carried out another exploration.
Among the most intriguing finds was the discovery of sulfur, an element whose presence on the Moon has been shrouded in mystery. The Laser-Induced Breakdown Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes tiny samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thereby revealing the presence of various elements, including sulfur. Sulfur on the Moon is a significant find. On Earth, sulfur is often associated with volcanic activity, raising questions about similar processes on the Moon in the past. Its presence could provide insight into the volcanic history of the Moon and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrayaan-3 was the search for water ice, a search that's intrigued scientists for decades. Water ice on the Moon is not just a scientific curiosity. It's a potential resource for future human missions, offering water for life support and fuel production. Despite high hopes, Chandrayaan-3, like its predecessors, found no direct evidence of water ice on the Moon's surface. However, the lack of direct evidence is not a conclusion, but a clue, leading to new hypotheses. One theory is coal trapping, in which water vapor can migrate to permanently shadowed craters of the poles, freezing into ice. The detection of sulfur adds another layer to this theory, as sulfur may be trapped with the water ice and released as a result of the breakdown of water molecules by high-energy solar radiation. The lack of direct evidence for the existence of water ice raises important questions. Is the ice deeper beneath the surface, shielded from detection by the insulating properties of the lunar soil?
Or is its prevalence more heterogeneous and elusive than previously thought? During its exploration of the Moon's south pole, Chandrayaan-3 found more than just sulfur. The rover's LIBS instrument made the first ever in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each element reflecting part of the complex geologic history of the lunar surface. Further measurements added new details to this discovery, further revealing the presence of calcium, silicon, and oxygen. These elements, each with its own unique spectral signature, provided clues to the formation of the Moon and its evolutionary history. Studies of the presence of hydrogen, a key component in the search for water, also continue. The mission's discovery of these elements and the ongoing search for water ice underscore the dynamic and complex nature of the Moon's geology. Each discovery, each unanswered question, moves us further in our quest to understand our nearest celestial neighbor, and prepares us for the next steps in lunar exploration. As the Chandrayaan-3 mission at the Moon's south pole opened a new chapter in lunar exploration, it also paved the way for the next ambitious leap: the Lunar Polar Exploration Mission, LUPEX for short. This joint venture between the Indian Space Research Organization and Japan Aerospace Exploration Agency is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the South Pole region of the Moon. JAXA will likely provide the H-3 launch vehicle and rover under development, and ISRO will provide the lander. This mission represents a significant step in international cooperation on lunar exploration. The mission's goals are multifaceted. It will demonstrate new surface exploration technologies critical for sustained lunar exploration in the polar regions. Precise landings will be achieved by using a feature-matching algorithm and navigation equipment derived from the JAXA Smart Lander for Investigating Moon mission. The LUPEX rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples from a depth of 5 feet, 1.5 meters. Finding and analyzing water are key goals of the mission, and the potential discovery of water ice could be a game-changer for future lunar missions. In parallel with LUPEX, ISRO's Chandrayaan-4 mission, designed to return samples from the Moon, is in the planning stage. Scheduled for launch by 2028, Chandrayaan-4 will consist of 4 modules: a transition module, a descent module, an ascent module, and a re-entry module. The ambitious goal of the planned mission is to return soil samples from the Moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, including sample collection, docking in lunar orbit, and returning samples to Earth.
Chandrayaan-3's innovative discoveries, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the Moon's mysterious nature. These results provide crucial insight into the Moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration is promising. Missions like LUPEX and Chandrayaan-4, building on the legacy of the previous ones, will continue to explore the mysteries of the Moon. India's role in these endeavors is not only that of a participant, but also that of a pioneer. Such events truly inspire us to look beyond the boundless mysteries of the cosmos. There are countless untold stories in the universe, but one mystery, veiled in the shadows of distant suns, stands out prominently among many others. This discovery invites us to look beyond earthly boundaries and ponder untold possibilities. This is the story of Kepler-22b, a planet that's not just wandering in the void, but basking in the sweet spot its star's habitable zone. Here, in this delicate balance,
all conditions exist to ignite the magic of life, for the water to flow freely and the atmosphere to hold the secrets of existence. Discovered by the gaze of the Kepler Space Telescope, Kepler 22b invites us to ponder what worlds may lie beyond our own, to question our understanding of life and our role in the universe. It makes us dream of new horizons, of distant shores where humanity may one day set foot. Today, we'll embark on a journey of discovery to unravel the mysteries of Kepler 22b and the countless other worlds that await us beyond our reach in the limitless expanse of space. In its search for Earth analogs scattered throughout the galaxy, the Kepler Space Telescope has become a pioneer, a celestial cartographer mapping the unknown. Initially, Kepler's mission was very clear: to observe the vastness of the Milky Way, looking for the faint twinkle of stars dimmed by the passing of planets in their orbit. Equipped with the most sensitive photometers, the telescope patiently watched the light of more than 150,000 stars. Among them, a pattern emerged: the rhythmic fadings of a particular star, not unlike our Sun. This was the first hint of Kepler 22b, a planet moving carefully around its star and briefly eclipsing its light, as if playing cosmic hide-and-seek. This discovery was a real event. The analytical skill required to sift through huge datasets and pick out planetary transits from the cacophony of cosmic noise was immense. It was akin to detecting a faint brightness difference caused by a moth flying in front of a lighthouse beam from thousands of miles away. The method of transits, Kepler's main tool, is a deceptively simple but very powerful technique. This method is based on the subtle interactions of planets orbiting their stars, passing in front of them for a moment and casting a small shadow, which then causes a slight dimming of the star's light. It's this faint, fleeting shadow that astronomers look for, a sure sign of a distant world orbiting its star. The elegance of the transit method lies in its simplicity and the wealth of information it provides. When a planet passes in front of its star, it blocks some of the starlight, causing a measurable dip in brightness. This dip, detected by instruments such as the Kepler photometer, is carefully analyzed to reveal not only the presence of a planet, but also its size. The amount of obscured light tells us how large a planet is compared to its star. Moreover, the regularity of these brightness variations reveals the planet's orbital period, the time it takes to complete one orbit around its star. This rhythm of disappearance and reappearance allows scientists to calculate how far away a planet is from its star, which provides crucial information about the planet's environment and its probability of habitation. This method also opens a window into the planet's atmosphere. When a star's light passes through a planet's atmosphere during transit, certain wavelengths of light are absorbed by atmospheric gases. By studying these changes in the star's spectrum, astronomers can determine the chemical composition of the planet's atmosphere, finding fingerprints of molecules that may indicate the presence of water, oxygen, or even signs of biological activity. The discovery of Kepler 22b was a watershed moment in the search for Earth analogs. It highlighted the incredible potential of our technology and the perseverance of scientists. This discovery has moved us further along the path of space exploration, opening new chapters in the history of the search for worlds that could one day become a second home for humanity.
In the variety of cosmic interactions between planets and stars, there is a delicate region, a narrow band where conditions are just perfect, where the hope of life as we know it lingers in the darkness. This region, known as the habitable zone, is a cradle for potential life, a haven where water can exist in a liquid state, neither boiling under the fierce light of a star nor freezing in the cold expanse of space. Imagine a world very similar to our Earth, located inside this life-supporting belt. Here, the heat from the star is neither too intense nor too weak, bathing the planet in soft light. And this is where Kepler 22b is, orbiting serenely in the habitable zone of its star, a prime candidate in the search for Earth-like conditions and possibly life beyond our solar system. Just as Earth thrives in the Sun's habitable zone, Kepler 22b enjoys a similar privilege, orbiting at a distance where temperatures can allow lakes, rivers, and oceans to exist.
The presence of liquid water, the universal solvent of many chemicals, is crucial, for it is in water that the chemistry of life unfolds. Water is the stage on which the drama of life is played out, from the simplest bacteria to the most complex forms of flora and fauna. Yet only the presence of water in a liquid state is one of the many conditions necessary to sustain life. What have we learned from analyzing this distant world, and is it so open to the theoretical presence of humans on it? As we dive into the mysteries of Kepler-22b, we embark on a journey of discovery, piecing together the puzzle of this distant world through the lens of our own Earth. With each observation, scientists are getting closer to understanding the fundamental nature of this distant planet, its size, its composition, and the very air that surrounds it. It's these factors that will help shed light on the presence of the basic components that may make this distant world a cradle for life. So, what are these factors? At the forefront of the search for life is, of course, the presence of liquid water, the cornerstone for all known biological processes on Earth. As we already know, Kepler-22b, which occupies a privileged position in the habitable zone, receives from its star a flow of energy that suggests that the temperature may be favorable for maintaining water in a liquid state. While the presence of liquid water is a promising start, the composition and behavior of Kepler-22b's atmosphere remains crucially unknown. Enveloping the planet, the atmosphere is the most important determinant of environmental conditions affecting temperature and surface pressure. Because the planet is in the habitable zone of its star, the theoretical presence of an atmosphere similar in composition to Earth's, rich in nitrogen and containing the requisite amount of oxygen and trace gases, could mean a temperate climate and stable water cycles similar to those that have nourished life on our home planet for billions of years. However, the range of possible atmospheric scenarios is enormous and shrouded in uncertainty due to our current technological limitations in directly observing exoplanet atmospheres at such great distances. If Kepler-22b's atmosphere tends toward a denser, carbon dioxide-dominated composition like that of Venus, this could lead to a greenhouse effect. In such a scenario, any potential water would exist as supercritical vapor at extreme pressures and temperatures. Conversely, an atmosphere that's too thin and free of greenhouse gases could turn Kepler-22b into a frigid world where water exists only as ice and the surface is exposed to harmful cosmic radiation. The equilibrium temperature of the planet, estimated at a comfortable 72 degrees Fahrenheit under Earth-like atmospheric conditions, indicates the possibility of an environment with ideal conditions for Earth-like life. However, if one were to go to the other extreme and create a Venus-like greenhouse effect, the surface temperature could soar to a scorching 860 degrees Fahrenheit, which would likely preclude the existence of life as we know it. Things get even more complicated. The elemental recipe for life goes beyond just water and the right atmosphere. Life as we know it is intricately woven from a variety of chemical elements, with carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur playing major roles. Sun-like stars, including Kepler-22, are G-type stars, and typically have similar proportions of hydrogen and helium, with a small amount of heavier elements playing a primary role. However, during planetary system formation, the distribution and concentration of materials in the protoplanetary disk around the nascent star influence the further composition of the forming planets. Temperature gradients in this disk lead to condensation of different materials at different distances from the star, which affects the composition of the planets. Once a planet is formed, its composition can be altered by differentiation, the separation of different materials within the planet, resulting in the formation of distinct layers such as the core, mantle, and crust, and geologic processes such as volcanic activity and plate tectonics. So, while direct measurements of the chemical composition of Kepler-22b are beyond our capabilities, the diversity of elements in the universe and the planet's location in a habitable zone can only hint at the exciting possibility of the presence of the building blocks that create the basis for the complex chemistry of life. While we wonder whether the planet's atmosphere might contain a protective layer like ours, or whether it's a dense, oppressive, cloak-trapping heat as a result of the greenhouse effect, and what the planet's chemical composition actually is, one thing we know for sure: the last, fourth parameter necessary for life is in almost perfect agreement. The complexity of life must necessarily be fueled by energy, and the presence of Kepler-22b in the habitable zone ensures its constant supply from the host star. This energy, which powers photosynthesis on Earth, could drive the fundamental biological processes necessary for life on this distant planet. The characteristics of a star that is slightly cooler and smaller than our Sun, but similar in many ways, provides a stable source of light and heat. Against the grand landscape of the cosmos, Kepler-22b stands out as a beacon of possibility, a world where the basic ingredients for life as we know it can come together. Yet the true nature of this distant planet remains shrouded in mystery, reminding us of the vast unknowns that await us as we continue to search for the secrets of the universe and the potential for life beyond our solar system. The search for signs of extraterrestrial life is the cornerstone of our celestial explorations, compelling us to venture into the unknown with hope and scientific rigor. As we turn our eyes toward distant worlds like Kepler-22b, the next generation of telescopes and space missions are poised to pierce the cosmic veil, inviting us to peer into the atmospheres of these distant planets and learn their secrets. At the forefront of this cosmic quest is the James Webb Space Telescope, the most sophisticated and powerful space telescope ever built. With unprecedented resolution and sensitivity, the JWST is designed to observe the universe in the infrared, enabling it to detect the faint reflections of light from the earliest stars and galaxies and, crucially, the atmospheric signatures of exoplanets. The JWST suite of instruments carefully analyzes light passing through the atmosphere of exoplanets as they transit their host stars. This process, known as transmission spectroscopy, will allow scientists to decipher the composition of the atmospheres of these worlds in search of characteristic signatures of molecules essential for life, such as water vapor, oxygen, and methane. The mission of the Transiting Exoplanet Survey Satellite, or TESS, launched in 2018 and complementing JWST, is to survey the brightest stars near Earth for transiting exoplanets. Building on the legacy of the Kepler mission, TESS is casting a wider net, revealing many new worlds for further study. Among them, planets that share characteristics with Kepler-22b will be prime targets for detailed atmospheric analysis, opening up new opportunities to search for biosignatures. Coming down to Earth, the Extremely Large Telescope, or ELT, which, when completed, will be the world's largest optical telescope, will be another powerful tool in the search for alien life. The ELT's colossal mirror, located atop Cerro Hermosones in Chile's Atacama Desert, will collect light from distant exoplanets, allowing direct images and spectroscopic studies of their atmospheres. Its advanced instruments will be able to detect even the faintest chemical fingerprints, further expanding our understanding of such distant worlds. Looking ahead, proposed missions such as the Habitable Exoplanet Observatory, HABEX, and the Large UV Optical IR Surveyor, LUVOIR, promise to push the boundaries of exoplanet research even further. Equipped with advanced technologies such as coronagraphs and star shades, these observatories aim to directly image exoplanets by dissecting their light to reveal the molecular composition of their atmospheres in unprecedented detail. The hunt for alien life embodied in exploring such planets continues to inspire and stimulate the human spirit, reminding us that the search for life beyond Earth is more than just a scientific endeavor. It's a profound exploration of our place in the cosmos. As we stand on the threshold of discovery, our thoughts drift to the distant world of Kepler-22b, a planet in the nourishing embrace of its star's habitable zone. Here, in this hypothetical realm, we imagine the possibilities such a world might hold. Could it be that the hilly landscapes of this distant planet are home to a diversity of alien flora thriving in the soft light of Kepler-22? Could it also be that its seas are teeming with life, with forms both strange and outlandish, adapted to the unique conditions of this distant world? And what is humanity's potential role in such a world? For now, it's hard to imagine, but these dreams are underpinned by the relentless pursuit of knowledge that defines our current path in exoplanet exploration. As we gaze into the heavens with instruments such as the James Webb Space Telescope, the Transiting Exoplanet Survey Satellite, and the upcoming of the Extremely Large Telescope, we continue to push the boundaries of our understanding. Each discovery adds its own piece to the great puzzle of the cosmos, revealing the diversity of worlds that inhabit our galactic neighborhood. The future of exoplanet exploration promises to deepen our understanding and knowledge of distant worlds, and redefine our place in the universe.
As we stand at this crossroads of imagination and discovery, we remind ourselves that the search for life beyond Earth and the understanding of humanity's future potential among the stars is a reflection of our deepest desires to explore, understand, and reconnect with the vast, wondrous cosmos that is our home. Amid the silent expanse of our solar system lurks a world of deep mystery and rugged beauty. Mars, with its purple dunes and ancient valleys, tells of its tantalizing past. It's a planet where sunsets color the sky blue, where towering dust devils run across the barren lands, and where the remnants of water streams silently tell the story of bygone days. Here, amid the red dust, lies the enigmatic brain terrain, a geologic marvel that defies explanation. Its intricate patterns, reminiscent of the complex folds of the human brain, remain one of Mars's most challenging mysteries. What forces created these enigmatic formations? Are they the key to unlocking the secrets of Mars's climactic past? As the sun dips below the horizon, the Martian sky transforms, casting blue light over the alien landscape. The scars of ancient rivers and cracks of dried mud tell a story of a time when water flowed freely on Mars, when the planet experienced the changing of seasons, and when this world may have been more Earth-like than we could have imagined. Yet for all of its wonders, Mars is a stark reminder of its alien nature. Today we'll travel to Mars, a world of beauty and mystery, a planet that holds the keys to our past and the promise of our future. Join us as we explore the mysteries of the good old red planet. Beneath the purple skies of Mars lies a canvas of geologic mysteries. Among them is the brain terrain. These complex patterns, reminiscent of the cerebral cortex, sprawl across the Martian mid-latitudes. Their origins are shrouded in mystery. What processes could have created such complex patterns? Scientists suggest that it's sublimation, the conversion of ice directly into vapor, that plays the key role here. Although the exact process remains cloaked in mystery, it's most likely the relentless interaction between the underground ice and the thin Martian atmosphere that forms the intricate patterns. But Mars is not a quiet world. It breathes and moves. Dust devils, those towering columns of cloying dust rising kilometers into the rarefied atmosphere, are not just a spectacle of nature, but the architects of the Martian surface. They crisscross barren landscapes, leaving behind dark trails that testify to their passage. These ethereal giants, born from the interaction of heat and wind, reach more than 2 miles in height and are larger and more dramatic than their celestial counterparts. And then, as the Martian day fades, the sky transforms. A Martian sunset bathes the landscape in an ethereal blue light that contrasts sharply with the familiar red and orange hues of daytime. This phenomenon arises due to the unique interaction of sunlight with the atmosphere of the red planet, filled with dust of iron particles. As it passes through, the red part of the visible spectrum of sunlight is scattered by the dust particles, leaving only a mesmerizing blue glow. Although this scattered light colors the sky red, at sunset and night, it transforms into shades of blue. But the mysteries of the Martian atmosphere don't end there. The interesting phenomenon of Mars's green glow recently captured by NASA's Odyssey orbiter, provides a glimpse into the unique characteristics of the Martian atmosphere. This glow, observed from orbit, is the result of atmospheric processes that are common throughout the solar system but manifest themselves differently on each planet due to variations in atmospheric composition and density. During the day, sunlight interacts with the Martian atmosphere, breaking down CO2 molecules through a process known as photodissociation. This releases individual atoms, which, when they hit the night side of the planet, recombine into different molecules while emitting light. On Earth, this phenomenon produces a whole spectrum of colors, but on Mars, the predominant color is green. This green glow is primarily due to the recombination of CO2 molecules in the upper atmosphere at an altitude of between 25 and 90 miles. Interesting studies have revealed an additional glow at lower altitudes, resulting from the recombination of oxygen atoms. This secondary glow, visible during the Martian summer, is concentrated in the polar regions, where atmospheric currents converge. The intensity of this glow varies with the time of year, alternating between the northern and southern hemispheres. The thinness of the Martian atmosphere compared to Earth's allows these luminous phenomena to be observed and studied more directly. It's also allowed the detection of other emissions, such as nitrogen oxide emissions in the ultraviolet spectrum, further enriching our understanding of the composition and behavior of the Martian atmosphere. Such atmospheric studies not only shed light on the processes that shape the Martian environment, but also provide valuable insights into the planet's past and present climatic conditions. Speaking of which, the Martian landscape, with its vast deserts and towering volcanoes, contains a wealth of clues about the planet's climatic past. Among them are signs of seasonal changes that have shaped the surface for millennia. The presence of features such as mud cracks, discovered by the Curiosity rover, which bear a striking resemblance to similar objects on Earth, suggests the presence of liquid water in the planet's past. In particular, the mud cracks are thought to have formed over many Martian seasons, indicating a cycle of wet and dry periods that Mars once experienced. Further evidence of Mars's dynamic climate can be found in the remains of ancient glaciers in the planet's mid-latitudes. These fossilized archives, imprinted into the Martian terrain, tell of a time when water ice slid across the planet's surface, carving furrows and transporting sedimentary rocks. These glaciers, like their terrestrial counterparts, shape the terrain, leaving behind traces of their presence in the form of moraines and carved valleys. Such activity suggests that Mars has undergone significant climatic changes, perhaps similar to the glacial and interglacial periods seen on Earth. The presence of sulfate in the mud cracks adds another layer to our understanding of Mars's water history. Mud cracks, like those found on Earth, are formed by the drying of sedimentary rocks, indicating the presence of standing water that periodically evaporates, leaving behind these prominent patterns, or subsiding beneath the surface. The detection of sulfates in these formations indicates that water interacted with the Martian soil, resulting in the deposition of minerals. The varying levels of these sulfates, combined with the pattern of mud cracks, paint a picture of a planet where water levels rose and fell, creating conditions conducive to chemical reactions that could even support the precursors of life. Clearly, it's the search for water on Mars that is a key aspect in understanding the planet's climate, geologic history, and potential for habitable life. Recent discoveries have shed light on the presence of water in various forms and locations on Mars, significantly changing our understanding of the red planet. On Mars, there are a great many geologic features that indicate the presence of water in the past. The discovery of ancient lake beds, river valleys, and outflow channels indicates that at one time, water flowed freely across the planet's surface. These features suggest that Mars once had a warmer and wetter climate, capable of supporting liquid water on its surface. The presence of sedimentary layers and mineral deposits in these ancient lakes and river valleys
further supports the idea of prolonged water activity that may have lasted thousands or even millions of years. One of the most revolutionary discoveries is the discovery of water ice near the equator of Mars. Traditionally, ice was thought to be found only in the polar regions of Mars, where it's visible on the surface.
However, radar surveys and analysis have revealed subsurface deposits of ice at lower latitudes, including near the equator. This refutes previous ideas about the climate of Mars and suggests that water ice is much more widespread across the planet than previously thought. The implications of equatorial ice extend to the climate history of Mars and its potential habitability. Equatorial ice deposits indicate a more complex hydrologic cycle on Mars than previously thought. This could mean that in the past, Mars had a climate more similar to Earth's, with water cycling between the atmosphere and the surface. However, such a presence does not at all raise the possibility that conditions suitable for life existed on Mars in the past, much less in the present. Water is a key component of life, but such a contrasting climate change cannot offer much chance for a long process of development of any life forms. The search for biosignatures, such as special minerals, organic molecules, or erosion patterns that may indicate past biological activity continues. Although no conclusive evidence of life on Mars has yet been found, the presence of water in various forms still retains a minimal possibility. Still, these water ice deposits could serve as a valuable resource for future human exploration and colonization of the planet, providing water for drinking, agriculture, and fuel production. Taking a closer look at the mineralogical landscape of Mars, we see that it's a stark contrast to the rich diversity found on Earth. About 6,000 different minerals have been discovered on our home planet, testifying to the dynamic geologic processes on Earth and the complex interaction between the biosphere and geosphere. These minerals have not only been formed by abiotic processes, but have also been significantly influenced by the presence of life, which has contributed to the diversity of minerals through various biochemical interactions. By comparison, after 5 decades of research, only 161 minerals have been identified on the Martian surface. This divergence in mineral diversity is not just a numerical gap. It tells us a lot about the differences in the geological activity and history of the two planets. The scarcity of minerals on Mars has profound implications for our understanding and the planet's potential to support life. The diversity of minerals on a planetary body is often a reflection of its geologic and environmental dynamism. On Earth, plate tectonics, water availability, and atmospheric processes contribute to the wide range of physical and chemical conditions that are so essential for the origin and maintenance of life. Complex organic molecules, including the precursors to DNA, often require diverse chemical environments and catalysts. The limited mineral diversity on Mars, therefore, raises some questions about the habitability of the planet as a whole. The lack of diverse minerals on Mars also indicates that the planet may have had a more monotonous geologic history compared to Earth. However, is it as quiet and peaceful as it appears? Recent studies of the internal structure of Mars have led to interesting discoveries, particularly through the analysis of seismic data. The InSight mission played a key role in this discovery before its completion, detecting what's believed to be the largest earthquake ever recorded on Mars. This earthquake, which lasted about 6 hours, did not fit the typical profile of a meteorite strike because no crater was left behind, suggesting it originated deep inside the planet. The magnitude of the quake, which was 4.7 on the Richter scale, hints at a significant geologic activity beneath the surface. Unlike Earth, Mars lacks plate tectonics, raising intriguing questions about the mechanisms causing these earthquakes. The lack of plate tectonics suggests that Martian earthquakes may be related to internal stresses or other geologic processes that we've not yet fully understood. Volcanic activity on Mars, both recent and ancient, has left indelible marks on its surface. Recent studies have found at least 40 different volcanic events, some of which occurred only a few million years ago. In addition, the discovery of unusual polygonal structures beneath the surface,
found by ground-penetrating radar from China's Shirong rover, indicates a history of thermal contraction and expansion and speaks to the planet's former volcanic activity. These structures, ranging in size from a few inches to a few feet, have been found at depths of about 100 feet. Obviously, a dramatic change in climate or some cataclysmic event has caused these deposits to be so deep beneath the planet's surface. The region known as Noctis Labyrinthus, with its vast network of valleys and canyons, is further evidence of Mars's volcanic past. Located near the volcanic Tharsis Plateau, home to the solar system's largest volcano, Olympus Mons, this region demonstrates the dramatic impact of volcanism on the Martian landscape. A video simulation provided by ESA shows how the stretching and bending of the Martian crust in this region, resulting in the formation of deep valleys and canyons, is evidence of the planet's active geologic past. The release of water during organic eruptions may explain the presence of ancient river valleys and lakes, providing a glimpse into times when Mars may have been more Earth-like, with a warmer and wetter climate. Understanding the planet's volcanic history not only sheds light on its past climate and potential for life, but also helps in future research, as regions with past volcanic activity may hold clues to the planet's habitability and the availability of vital resources. Speaking of livability, it's impossible not to mention the recent successes in the production of oxygen on Mars. The Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, was an achievement in space technology, successfully producing oxygen from Mars's carbon dioxide-laden atmosphere. Installed aboard NASA's Perseverance rover, MOXIE operates efficiently in a variety of Martian conditions, both day and night, and in different weather states of the planet's atmosphere. Its ability to convert CO2 into oxygen through the process of solid oxide electrolysis is a significant technological achievement. By heating the Martian atmosphere to 800 degrees Celsius, MOXIE decomposes CO2 into oxygen ions and carbon monoxide, and then recombines the oxygen ions into breathable O2. This process has been shown to achieve the required oxygen production and purity despite design trade-offs due to the mass, power, volume, and cost constraints associated with space missions. The success of MOXIE has profound implications for the future of human exploration and potential colonization of Mars. The ability to produce oxygen on Mars paves the way for a sustainable human presence, reducing dependence on Earth for critical life support resources. The study concludes that a large-scale version of MOXIE could generate tens of tons of oxygen, essential not only for astronauts' life support, but also as a critical component of rocket fuel. Such a capability would significantly reduce the logistical and financial burden of transporting oxygen from Earth to Mars, which would otherwise require launching hundreds of tons of the material into space at an exorbitant cost. By providing a reliable supply of oxygen, systems like MOXIE could support longer missions, larger crews, and even permanent settlements on Mars. In addition, the technology can be adapted to produce other necessary resources, such as water and fuel, taking a significant step toward realizing the dream of a self-sufficient human presence on the Red Planet. Speaking of the Perseverance rover, we should also mention its Ingenuity helicopter, which has far exceeded the original parameters of its mission on the Martian surface. Built just for a brief technology demonstration, Ingenuity was only supposed to make 3 flights within 30 days. However, it shattered those expectations by flying 72 missions over more than 1,000 Martian days, demonstrating its resilience and adaptability to the harsh Martian environment. This achievement was not only an important milestone in the aerial exploration of other planets, but also laid the groundwork for future missions. Ingenuity's journey was not without its challenges. It encountered and overcame numerous technical problems, including communication outages and unexpected landing scenarios. Despite these challenges, Ingenuity continued to push the limits of what was possible and even set a new range record on one of its flights. The vehicle's ability to survive and operate through Martian dust storms, extreme temperatures, and even sensor failure speaks to the reliability of its design and the team's careful planning. However,
The mission ended in an unforeseen way when a significant part of the blade of one of Ingenuity's rotors was damaged, making further flight impossible. This incident marked the official end of Ingenuity's Mars mission. The helicopter's final flight took place in January 2024. However, the termination of Ingenuity's missions does not take away from its outstanding achievements and the invaluable data it provided. NASA has already begun applying lessons learned from operating aircraft in extraterrestrial environments to upcoming missions, including the Dragonfly mission to Titan, Saturn's largest moon.
The success of Ingenuity has opened the door to more ambitious use of aircraft for tasks such as sample retrieval, which could significantly increase the efficiency and scope of exploration of other planets. During its long stay on the Red Planet, the Perseverance rover has accumulated a considerable amount of samples of Martian rock materials. However, it's worth noting that the endeavor to return samples from Mars to Earth is both the pinnacle of scientific endeavor and the nadir of logistical challenges. The financial implications are staggering. According to recent estimates, the costs could exceed those of the most expensive space missions, such as the James Webb Space Telescope, totaling up to $11 billion. The complexity of safely extracting samples from the Martian surface and transporting them back to Earth involves multiple spacecraft and precise robotic operations. This task requires not only unprecedented precision engineering and navigation solutions, but also significant financial outlays, which raises questions about budget allocation and priorities in space exploration. When it comes to prioritizing space exploration, humanity faces another unresolved challenge. The ongoing debate over international cooperation in Mars exploration is multifaceted, involving political, scientific, and logistical considerations. On the one hand, cooperation can pool resources, share risks, and increase the scientific return on missions through diverse expertise. On the other hand, comparing the successes of collaborative efforts, such as the International Space Station, against the backdrop of some international constraints, highlights the contradiction between the ideal of a united human effort in space exploration and the reality of international relations on Earth. Another, but not the last, test in our path is that as Mars becomes a center of exploration and potential colonization, the problem of space debris is becoming increasingly important. Debris accumulation in Martian orbit can pose a hazard to spacecraft, impede navigation, and jeopardize missions. This problem is not just theoretical. The proliferation of debris around Earth has already created an urgent need for sophisticated tracking and avoidance maneuvers. In turn, solving this problem on Mars will require proactive measures to prevent the accumulation of debris and possibly the development of debris reduction and removal technologies to ensure the safety and sustainability of future missions. Mars colonization, once the stuff of science fiction, is increasingly entering the realm of possibility thanks to technological advances and scientific discoveries. The success of Ingenuity has opened the door to more ambitious use of aircraft for tasks such as sample retrieval, which could significantly increase the efficiency and scope of exploration of other planets. During its long stay on the Red Planet, the Perseverance rover has accumulated a considerable amount of samples of Martian rock materials. However, it's worth noting that the endeavor to return samples from Mars to Earth is both the pinnacle of scientific endeavor and the nadir of logistical challenges. The financial implications are staggering. According to recent estimates, the costs could exceed those of the most expensive space missions, such as the James Webb Space Telescope, totaling up to $11 billion. The complexity of safely extracting samples from the Martian surface and transporting them back to Earth
involves multiple spacecraft and precise robotic operations. This task requires not only unprecedented precision engineering and navigation solutions, but also significant financial outlays, which raises questions about budget allocation and priorities in space exploration. When it comes to prioritizing space exploration, humanity faces another unresolved challenge. The ongoing debate over international cooperation in Mars exploration is multifaceted, involving political, scientific, and logistical considerations. On the one hand, cooperation can pool resources, share risks, and increase the scientific return on missions through diverse expertise. On the other hand, comparing the successes of collaborative efforts, such as the International Space Station, against the backdrop of some international constraints, highlights the contradiction between the ideal of a united human effort in space exploration and the reality of international relations on Earth. Another, but not the last, test in our path is that as Mars becomes a center of exploration and potential colonization, the problem of space debris is becoming increasingly important. Debris accumulation in Martian orbit can pose a hazard to spacecraft, impede navigation, and jeopardize missions. This problem is not just theoretical. The proliferation of debris around Earth has already created an urgent need for sophisticated tracking and avoidance maneuvers. In turn, solving this problem on Mars will require proactive measures to prevent the accumulation of debris and possibly the development of debris reduction and removal technologies to ensure the safety and sustainability of future missions. Mars colonization, once the stuff of science fiction, is increasingly entering the realm of possibility thanks to technological advances and scientific discoveries.
So, why did scientists initially hypothesize the possibility that this star would be the next observed supernova? This giant occupies a prominent place in the constellation of Orion, perched on its shoulder, and is visible to the observer even to the naked eye. Let's take a look at the life cycle of Betelgeuse, an intriguing journey that will show the evolution of the star from its birth to its current state as a massive, pulsating giant nearing the end of its life. Betelgeuse began its existence as a massive star burning hydrogen in its core, like many others. However, because of its large mass, it evolved rapidly, entering successive phases of nuclear fusion. The significant mass of the star distinguished its evolutionary path from the evolution of smaller stars, such as our Sun. While the Sun is currently a stable main sequence star, slowly converting hydrogen into helium, Betelgeuse, due to its much larger mass, more quickly depleted its hydrogen reserves and evolved into a red supergiant. The key difference between Betelgeuse and our Sun is their masses. Betelgeuse, which has about 15 to 20 times the mass of the Sun, experiences higher pressure and temperature in its core, which accelerates nuclear fusion. Intense fusion causes Betelgeuse to burn its fuel rapidly, resulting in unstable structure and significant brightness fluctuations. In contrast, the Sun's lower mass allows it to remain stable for billions of years, with a much longer and more stable hydrogen burning phase. As Betelgeuse aged, it entered successive phases of nuclear fusion, gradually burning off elements heavier than hydrogen. Internal pressure caused the star to begin to swell, transforming it from a main sequence star into a red supergiant. This stage is characterized by Betelgeuse's enormous size and variability in brightness. The star expands and contracts as it undergoes complex nuclear processes. Recent observations have suggested that Betelgeuse may be on the verge of a supernova. The star's dimming in 2019, followed by an unexpected increase in brightness, has led scientists to speculate that it may be approaching the final stage of its life. These changes in brightness are thought to be related to internal processes, possibly signaling the beginning of core collapse. The star's pulsations, with cycles of 185, 230, 420, and 2,200 days, were analyzed to understand its internal dynamics.
The longest cycle of 2,200 days is particularly intriguing because it may represent Betelgeuse's fundamental pulsation mode, indicating its advanced stage of evolution. These observations, along with recent telescopic findings, suggest that Betelgeuse may be entering a phase of carbon combustion that precedes a supernova explosion. But what are the complex nuclear processes that dictate when a star's life must come to an end? At the center of a massive star like Betelgeuse, nuclear fusion turns hydrogen into helium, releasing enormous energy. As the star ages, heavier and heavier elements fuse to form bulb-like layers. Eventually, the core is filled with iron, which cannot release energy during the fusion process, leading to gravitational collapse. As the core collapses, a runaway reaction is triggered. In this process, the iron core collapses under enormous gravitational forces, reaching temperatures of billions of degrees. This leads to the rebound effect, where the core inflates and then explodes, creating a shockwave that rips the star apart. A supernova explosion releases an enormous amount of energy, briefly eclipsing an entire galaxy. The mechanics of this process involve a complex interplay between nuclear collapse, gravitational forces, and intense heating. The shock wave generated by the collapse of the core propagates outward, ejecting the outer layers of the star into space. Ancient astronomers have recorded these bright phenomena for thousands of years, sometimes describing them as guest stars, new stars. The earliest recorded supernova observation dates back to 185 AD, when Chinese astronomers observed guest stars, as they called them, that were visible for 8 months. Although rare, astronomers continue to study them to this day, especially when they lead to unusual phenomena such as gamma-ray bursts. Gamma-ray bursts, or GRBS, are intense bursts of gamma rays, usually associated with the collapse of massive stars or the merger of neutron stars.
Recent research suggests that Betelgeuse's cycles of dimness and brightness are part of its natural behavior as a variable star. It turns out that, unlike our Sun, Betelgeuse is an extremely explosive and low-density plasma cloud that changes shape frequently. Created by scientists, simulation illustrates the behavior of Betelgeuse in time. Periods of brightness and dimness occur about every 400 days, and the longer cycle is about 2,000 days. Recent studies have tried to explain the great dimming phenomena that occurred in 2020, and observations from various telescopes over the past 15 years have provided much insight. Observations at various frequencies, including microwaves and infrared, have allowed scientists to penetrate the layers of Betelgeuse and detect silicon monoxide, indicating the presence of a large dust cloud. This discovery disproved initial speculation that Betelgeuse was about to explode. Instead, it appears that internal activity within the star has caused the material to separate, forming a large gas cloud. The formation of a cold region beneath this cloud caused particles to condense, creating a dark cloud that obscured Betelgeuse from view from Earth. Further study of Betelgeuse's behavior revealed that the star experienced 2 shock waves, one in 2018 and another 1 year later. These waves disrupted the surface, creating hot and cold spots, which was confirmed by Hubble Space Telescope ultraviolet imaging observations. The shock waves and their aftermath disproved the initial assumption that Betelgeuse was close to a supernova, and instead showed that this behavior of the star is part of its natural life cycle. Betelgeuse's behavior is also characterized by its high rotation rate. Unlike typical red supergiants, which rotate slowly, Betelgeuse rotates at about 3 miles per second, which initially led researchers to think that it might have been a binary star that collided. However, recent research suggests that this rotational speed may be influenced by fast-moving convective cells inside the star, contradicting initial assumptions about its rotational behavior. Despite the unusual behavior,
This research suggests that Betelgeuse is unlikely to become a supernova in our lifetime. The current state of the star is more like a variable red supergiant, nearing the end of its life, but by no means approaching a supernova explosion. So, finally, we come to the very question that concerns all of us. How would such an explosion affect our home planet? The potential impact of a nearby supernova on Earth is a subject of speculation and concern. While a supernova is not expected to pose an immediate threat to our home, the explosion of a star within a few light years could affect Earth's atmosphere and potentially impact life. For example, the flare of the very same BOAP-GRB was so intense that it significantly affected the Earth's ionosphere, altering atmospheric conditions and disrupting radio communications. The flash released a tremendous amount of energy that interacted with the Earth's atmosphere, causing a sudden increase in ionization. This increased ionization affected the ozone layer and triggered chemical reactions that scientists are still trying to understand. The GRB also disrupted radio signals, especially those used for communication and navigation. The energy released in the explosion was so great that it even blinded several satellites, demonstrating the enormous power of these cosmic phenomena. However, the burst itself was observed from a galaxy a whopping 2.4 billion light-years away. This event only emphasizes the need for further study of gamma-ray bursts to understand their impact on us, our planet, and the universe as a whole. In addition, supernova studies also contribute to our understanding of dark matter, dark energy, and the overall structure of the universe. Type Ia supernovae, which occur in binary star systems, are crucial for measuring cosmic distances and studying the expansion of the universe. These standard candles have helped astronomers detect the accelerating expansion of the universe, which, in turn, has provided the background for understanding dark energy. Supernovae are a key focus of future astronomy. Their explosive nature and transformative impact continues to fascinate scientists and inspire discovery. Well, while some people are frozen in anticipation of the Betelgeuse explosion on live internet feeds, we look forward to discoveries from missions such as the Vera Rubin Observatory and the European Space Agency's Euclid telescope, which will contribute to advancing our understanding of supernovae.
As we look deeper into space, these stellar explosions will undoubtedly shape our understanding of the universe and our place in it. In the vast, silent expanse of our solar system, beyond the familiar brilliance of Neptune, rumors of some unseen presence have been stirring astronomers for quite a few years now. This mysterious force, unseen but undeniable, stretches the very fabric of our cosmic neighborhood, bending the paths of distant objects with its invisible grip. Here in the shadowy depths of space, where the warmth of the sun barely reaches, lies a mystery that's baffled the brightest minds. The hypothetical world known only as Planet 9, whose existence can be determined not by direct observation, but only by the subtle interaction of trans-Neptunian objects performing complex orbital motion. Could there be a rogue planet, shrouded in the darkness of space, exerting its influence from afar? A world that defies our understanding and challenges the very limits of what we know about our solar system. Join us as we piece together clues scattered in the back of the solar system in search of a planet that has so far eluded our sight. In the early 1990s, the outer reaches of our solar system began to reveal their secrets. Astronomers discovered a region teeming with icy bodies, now known as the Kuiper Belt. This discovery marked the beginning of a new chapter in our cosmic journey, expanding our understanding of the boundaries of the solar system. Among these distant wanderers was Pluto, long considered the 9th planet and proudly bearing that title since its discovery in 1930. But as the Kuiper Belt uncovered its treasures, Pluto's status began to be questioned. The discovery of objects such as Eris, that rivaled and even surpassed Pluto in size, sparked a debate that shook the foundations of planetary classification. In 2006, the International Astronomical Union was faced with an unresolved situation. What defines a planet? The answer to this question led to a controversial decision that downgraded Pluto to a dwarf planet. This decision, met with both approval and opposition, has swept through the astronomical community and the public, redefining the way we think about the solar system. In this cosmic controversy, however, the seeds of a new mystery were sown. The peculiar orbits of some Kuiper Belt objects, including the then-distant, newly discovered Setna, hinted at an invisible influence from the shadows guiding these icy bodies. Could it be that another planet, hidden in the vastness of space, created the architecture of the outer solar system? This question ignited the imagination of astronomers like Mike Brown and Konstantin Batygin, who set out to find the truth. Their journey will lead them to speculate on the existence of Planet 9, a hypothetical world hiding behind Neptune, whose presence is signaled only by the interaction of the most distant members of the Kuiper Belt. A new planet emerging from the heart of controversy awaits discovery. As we move beyond the familiar boundaries of the inner solar system, a realm of icy bodies and distant orbits opens up before us. Here, in the cold, dark regions beyond Neptune, lies an enigma that has captivated astronomers for years. It's the Kuiper Belt, a vast ring of debris left over from the formation of the solar system. Among these celestial wanderers, a separate group shows peculiar behavior that contradicts the expected norms of orbital mechanics. These are detached TNOs, or trans-Neptunian objects, whose paths are free of Neptune's gravitational influence, and extreme trans-Neptunian objects, or ETNOs, whose orbits are so eccentric that they seem to be tethered to some invisible force. What could be the architect of this unusual behavior? The answer may lie in the gravitational anomalies that pervade this distant region. These anomalies, subtle but deep, indicate the presence of a massive object whose gravitational pull shapes the orbits of these distant objects. The detached TNOs, whose orbits seem to be unaffected by Neptune, hint at a disturbance in the gravitational harmony of the outer solar system. Meanwhile, ETNOs, with their extreme orbits, paint a picture of cosmic interaction guided by a hidden force. The quest to understand these gravitational mysteries led researchers to hypothesize the existence of Planet 9, a hypothetical world whose mass and orbit could explain these anomalies. By carefully mapping the orbits of these mysterious objects, scientists began piecing together the potential location and characteristics of this invisible planet. In the tranquil balance of our solar system, each planet plays its part, revolving around the sun in a centuries and centuries and centuries old rhythm. But beyond this familiar rhythm looms a shadowy figure, a silent participant whose presence is felt but not seen.
Let's take a closer look at the Planet 9 hypothesis itself. In 2014, astronomers Chad Crickio and Scott S. Shepard noted an intriguing similarity between the orbits of Sedna, 2012 VP 113, and several other ETNOs, a phenomenon too unusual to be a mere coincidence. Crickio and Shepard made a bold suggestion: the existence of an unknown planet whose orbit is a perfect circle between 200 and 300 astronomical units from the Sun. A few years later, in 2016, Mike Brown and Konstantin Batygin embarked on an intellectual journey, delving into the mysteries of the outer solar system in order to develop this hypothesis. Through careful analysis and computational modeling, Brown and Batygin pieced together previously found gravitational anomalies that indicated the existence of a massive, invisible planet. This hypothetical world, in their opinion, could be the key to unraveling the special dynamics of the outer part of the solar system. As their research progressed, so did their understanding of the potential characteristics of Planet 9. Its mass was originally thought to be 10 times that of Earth, but further research revealed that its mass was slightly less, but still significant at about 5 or 6 Earth masses.
This revision painted a picture of a planet powerful enough to control the orbits of distant objects, yet elusive enough to remain hidden from our most powerful telescopes. The influence of this hypothetical planet extends far beyond its immediate vicinity. Its gravitational influence can explain the clustering of the orbits of detached TNOs and the extreme trajectories of ETNOs, weaving together a complex picture of celestial mechanics. The hypothesis of Planet 9 sparked a flurry of scientific research, and astronomers around the world joined the hunt for this elusive neighbor. The search for Planet 9 is a journey fraught with difficulty, a testament to both the vastness of the universe and the limitations of our current technological capabilities. Its distant orbit, presumably huge and elliptical, leads it through the farthest reaches of our system. This region, where the light of the sun is almost unattainable, envelops the planet in total darkness. This remoteness poses a serious problem because the potential position of the planet can encompass vast portions of the sky, requiring extensive, focused searches covering these celestial expanses in painstaking detail. It's something akin to trying to find a needle in an astronomical haystack. Moreover, because of its distance from the sun, the planet's surface temperature is extremely low, meaning it emits minimal thermal radiation, making infrared detection just as difficult. The lack of emitted and reflected light is compounded by the glare of distant stars and the myriad cosmic objects that fill the sky, each vying for the attention of our telescopes.
Among other difficulties, the nature of the search is compounded by the planet's enormous orbital period, which is thought to be thousands of years, because the planet's motion across the sky is imperceptibly slow from our earthly perspective. Even after a decade, Planet 9's position in space will have changed only slightly, making any attempt to observe its motion in the short term virtually impossible. This chilling rate of motion means that traditional methods of detecting planets by observing their transit or motion against the background of stars are not feasible. However, in their relentless pursuit, astronomers use an array of sophisticated techniques and instruments, from ground-based telescopes equipped with advanced adaptive optics to space-based observatories that circumvent the Earth's atmospheric distortions. So, in the pursuit of Planet 9, astronomers have had to go beyond traditional observational methods, leading to the development of several innovative approaches aimed at refining the elusive planet's location. They utilize unique aspects of the solar system's external environment and potential celestial interactions that Planet 9 may have with other objects. One of the proposed approaches has to do with potential moons that may orbit around Planet 9. Given its considerable mass, it is conceivable that it could have captured one or more moons during its long journey through the solar system. The concept is based on the process of tidal heating, a phenomenon in which the gravitational interaction between a planet and its moon causes internal heat to be released within the moon, potentially making it warmer than the parent planet. This is what allows the satellites Europa and Enceladus to have liquid subsurface oceans, and also provokes vigorous volcanic activity on Io. This internal heating may cause the moons to emit infrared radiation more perceptively than Planet 9 itself, providing an indirect but promising avenue for detection. Another innovative method involves tracking the trajectories of interstellar asteroids passing through our solar system. These high-speed objects coming from regions outside our solar system could potentially be affected by the gravitational pull of Planet 9. By meticulously tracking the trajectories of such asteroids, astronomers can infer the presence and location of a planet from the subtle gravitational jolts it exerts on passing bodies. This method was demonstrated by studying the interstellar asteroid Oumuamua, whose path through our solar system may have been slightly altered by such a massive object. The trajectories of spacecraft passing through the outer solar system can also provide valuable insights. Like asteroids, when spacecraft travel vast distances between planets, their trajectories are slightly and subtly influenced by the gravitational forces they encounter. By analyzing the precise tracking data from these missions, scientists can detect unaccounted gravitational anomalies that may hint at the presence of Planet 9. This method requires accumulating huge amounts of data over long periods, because the gravitational effects are incredibly subtle. However, the results can be very significant and will pay off the time spent. Moving from direct observation to indirect detection through a planet's influence on its environment may be the key to unlocking one of the greatest mysteries of our cosmic neighborhood. The search for Planet 9 has also spawned many theories and speculations about the true nature of this elusive object. Among the most intriguing are hypotheses that Planet 9 could be a primordial black hole or a dense dark matter clump, each representing a radical departure from the traditional planetary view. The idea that Planet 9 could be a primordial black hole introduces a sharp change of narrative. Unlike stellar black holes formed by the collapse of massive stars, primordial black holes are theorized to have originated in a high-density environment shortly after the Big Bang. These hypothetical entities may be the size of an asteroid, but have the mass of a planet. The possibility that Planet 9 is one of these ancient, mysterious objects is compelling for several reasons. First, it would allow us to explain the gravitational effects attributed to it without the need for a visible planetary body. Secondly, this of course does not completely contradict the impossibility of its detection, since such an object would theoretically be no larger than a basketball. According to another theory, Planet 9 may be a concentrated blob of dark matter. This form of matter, which does not emit, absorb, or reflect light, accounts for a significant portion of the total mass of the universe, but remains one of the greatest mysteries. Dark matter clumps, theoretical clusters of dark matter, are thought to have arisen from density fluctuations in the early universe.
As the universe expanded and cooled, these gravitational fluctuations led to the formation of dark matter structures, ranging from small clumps to massive halos surrounding galaxies. If Planet 9 were a dense cluster of dark matter, it could exert the gravitational influence observed in the outer solar system without being directly observable, using conventional telescopic techniques. The primordial black hole and dark matter clot hypotheses emphasize the profound implications of the search for Planet 9, far beyond the discovery of a new member of the solar system. Whether it's an ordinary planet, a primordial black hole, or a dark matter clot, one way or another, we'll find ourselves on the favorable side of events. The search for Planet 9 is a testament to humanity's enduring curiosity and relentless pursuit of the unknown. A recent preprint of a research paper by the same Mike Brown and Konstantin Batygin and their colleague Matthew J. Holman, entitled Pan-STARRS 1 Search for Planet 9, dated February 1, 2024, reflects the meticulous, ongoing efforts to uncover this enigmatic member of our solar system. The study used extensive data from the Pan-STARRS 1 survey, which, with its deep and wide sky coverage, provided a unique vantage point for the search. By focusing on single-night transients and using a sophisticated Keplerian orbit-linking algorithm, the researchers sifted through billions of detected objects, a task akin to finding a single grain of sand among the entire North American coastline. This methodological approach represents a significant leap forward, building on the foundation laid by previous surveys such as the Zwicky Transient Facility and the Dark Energy Survey. Despite the depth and breadth of the PS1 survey, the elusive ninth planet remained out of sight. No features matching the search parameters were found in the data. This result, while not leading to the discovery of a ninth planet, nevertheless narrowed the search area considerably, excluding 78% of the parameter space in which the planet could potentially reside. The remaining 22%, areas with poor observational coverage or inaccessible to current detection capabilities, represent the next frontier in the space search. The journey doesn't end with the PS1 research. The upcoming launch of the Vera C. Rubin Observatory promises to usher in a new era of astronomical observation, with capabilities that can finally pierce the veil of mystery, including that which surrounds Planet 9. As we stand on the threshold of these future explorations, the search for Planet 9 remains a beacon of scientific inquiry, a reminder of the vastness of the universe and the small but significant place we occupy in it. In the shadowy depths of our solar system, far beyond the last known gas giant, lies a world shrouded in intrigue and mystery. This is Pluto. Once considered the ninth planet, it now occupies a separate category, at the center of heated debate and scientific curiosity.
For decades, Pluto remained a blurry speck of light in our most powerful telescopes, a distant dot at the edge of our vision. It was a world waiting to be discovered, keeping its secrets in the cold, dark depths of space. At the dawn of the 21st century, an unprecedentedly ambitious mission began. The New Horizons spacecraft embarked on a billion-mile journey to explore Pluto's icy frontiers. What it discovered was astonishing in its diversity. Towering ice mountains, huge nitrogen glaciers, and the legendary heart-shaped Tombaugh ratio, an object so large it can be seen from space. But these discoveries are just the beginning. Join us as we journey together into the icy depths of the outer solar system, where one dwarf planet is eagerly waiting to tell us its story. In the early 20th century, the search for a ninth planet, the mysterious Planet X, gripped the world of astronomy. This search was not just about adding another name to the list of planets. It was about understanding the unseen forces that shape the orbits of the then already known celestial bodies around us. At the center of this search was Lowell Observatory in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on a painstaking journey through space. Armed with a telescope and photographic plates, Tombaugh set out to scrutinize the night sky, inch by inch, in search of an elusive planet that eluded detection. On a February night in 1930, Tombaugh's diligence paid off. Among the countless stars, he spotted a moving object, a tiny speck of light that was unlike anything else he had observed. It was Pluto, a distant world named after the Roman god of the underworld, a discovery that would change the boundaries of our solar system. As the decades passed, Hubble's Space Telescope brought us closer to Pluto than ever before. Launched into orbit in 1990, Hubble's powerful lens pierced the veil of distance separating us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a mere glowing dot to a world with distinct features. These Hubble images provided the basis for a more detailed study. They showed Pluto's complex surface, marked by variations in brightness and color, hinting at a dynamic world waiting to be explored. An odyssey of discovery that began with a single blinking dot on a photographic plate has brought us to the threshold of a new frontier. Pluto, once a mere curiosity at the edge of our solar system, was about to reveal its secrets through a relentless pursuit of knowledge and a relentless spirit of exploration. 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond. In January 2006, humanity embarked on another of its most ambitious journeys. New Horizons, a spacecraft no bigger than a grand piano, was poised across the vast emptiness of space, heading for a world barely seen by human eyes. Its mission is to unlock the secrets of Pluto, a mysterious dwarf planet at the edge of our solar system. When New Horizons soared into the sky, it carried the aspirations of countless people who had devoted years to that moment. The journey was a marathon of cosmic proportions, spanning nearly a decade and more than 3 billion miles. With precision, it plotted a path through the void, guided by the gravitational slingshots of celestial bodies in its path. In 2015, after 9 long years, as New Horizons approached its distant destination, the whole world watched with bated breath. The first images were simply revolutionary. Pluto, which was once just a speck of light even in the most powerful telescopes, now appeared to be a world of mountains, valleys, and plains. The landscape that came into view was strikingly varied. Ice mountains, some as tall as the Rockies, rose proudly to the surface, their peaks shrouded in a blanket of methane snow. Sputnik Palladia, a nitrogen ice plain, stretched across the entire dwarf planet, its surface mottled with a complex pattern of ridges and depressions. Among the most striking discoveries are signs of geological activity. Pluto, long thought to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice slowly flowed across the landscape, and hints of cryovolcanoes indicated that this distant world was not as inactive as previously thought. New horizons leap into the unknown, bridge the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes. It was a dynamic world full of surprises and beauty waiting at the edge of our solar system. It was just the beginning of a new chapter in our understanding of the cosmos. Pluto's expanse of rugged landscapes is home to one of its most mesmerizing features, the Sputnik Palladia. This enormous heart-shaped glacier is not just a striking visual landmark, it's a geological marvel that's changed the way we think about this distant world. The origin of Sputnik Palladia is a story of cosmic forces. This vast basin, stretching more than 650 miles, is believed to have been formed by the impact of a massive celestial body, an event that changed Pluto's surface and possibly its entire geology. The basin was filled with various ices, mostly nitrogen, creating a smooth, reflective plain that contrasts sharply with the surrounding topography. The surface of Sputnik Palladia is modeled with a complex pattern of convection cells, each the size of a country on Earth.
These cells are the surface manifestation of ice in slow motion, turning and flowing in response to the weak heat coming from Pluto's interior. This lava lamp-like process shows that Pluto is far from the inert, frozen world we once imagined. More mysteries lie beneath the icy facade of Sputnik Palladia. The uniform mass distribution in this region, obtained from spacecraft measurements, hints at the presence of a denser layer beneath the ice. Scientists speculate that this may be a subsurface ocean. It's possible that this reservoir could contain liquid water, isolated by the ice crust above. Among other discoveries, scientists have also found that Pluto has an atmosphere, hovering above its icy surface. As thin and fragile as an atmosphere can be on the cold fringes of the solar system, composed mostly of nitrogen, with traces of methane and carbon monoxide, this thin veil provides clues to understanding the planet's most mysterious processes. The structure of the planet's atmosphere does not match the primary expectations. When New Horizons flew by, it found an atmosphere extending hundreds of miles above the surface, much more extensive than expected. This thin atmospheric layer is stratified and has a complex interplay of gases that scatter and refract sunlight, creating a mesmerizing blue hue that resembles Earth's own sky. Because Pluto's journey around the Sun is unlike any other planet in our solar system, with an orbital period of an unimaginable 248 Earth years, each season on Pluto can last decades. Its trajectory is markedly elliptical. It is much closer to the Sun at perihelion than at aphelion, and its axis is tilted at an angle of 120 degrees, resulting in extreme seasonal variations on its surface. As Pluto approaches its perihelion, the heat from the distant Sun, though faint, is enough to cause a remarkable transformation. Surface ices, composed of nitrogen, methane, and carbon monoxide, begin to sublimate, a process by which these ice change from a solid state to a gaseous state, without changing to an intermediate liquid state. This sublimation is most pronounced in regions exposed to the Sun's weak but constant rays, resulting in an increase in atmospheric pressure, as gases, previously trapped in ice form, are released to the outside. This outgassing thickens Pluto's atmosphere, making it more substantial during these warm periods. The atmosphere expands, rising hundreds of kilometers above the surface, much more than during colder periods. This expansion is uneven, and it's influenced by Pluto's topography and the composition of its ice, creating a complex and dynamic atmospheric system. As Pluto continues its long journey, moving away from the Sun and toward more distant parts of its orbit, the atmosphere is undergoing a dramatic turn of events.
The gases that once thickened the atmosphere are now cooling and condensing, falling back to the surface as a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining feature of Pluto's climate, changing its surface over the centuries. This dance of ice and vapor unfolding over the course of Pluto's long year paints a portrait of a world in constant motion. Far from a static, frozen wasteland, Pluto's surface is a dynamic environment, a reminder of the active and ever-changing nature of even the most distant members of our solar system. Another exciting discovery about Pluto's atmosphere is its escape rate. Unlike the strong magnetic fields and gravitational pull that protect the atmosphere of the larger planets, Pluto's weak gravity allows much of its atmosphere to escape into space. This atmospheric escape contributes to the ionized gas tail, an invisible comet-like trail that Pluto leaves behind it as it orbits the Sun. This leakage is not a steady, gentle flow, but a complex interaction with a solar wind, a stream of charged particles emanating from the Sun. These particles, colliding with escaping atmospheric gases, create a dynamic and ever-changing environment around Pluto, a miniature magnetosphere in which the drama of solar and planetary forces is played out. From Pluto's dynamic atmosphere and unique climate, we move to its largest moon, Charon, and discover relationships and landscapes that change the very definition of celestial bodies in the outer part of our solar system. Charon, Pluto's largest satellite, orbits in synchronized motion with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It is a whole world filled with geological wonders and a unique history that's intertwined with that of Pluto. As New Horizons flew past Charon, they saw a landscape of canyons so deep and wide they could easily swallow up parts of Earth's Grand Canyon. These chasms stretched across the surface of a satellite, telling a story of geologic upheaval. Mountains rising dramatically against the lunar surface reveal a dynamic history, their peaks casting long shadows over the valleys below. The origins of Charon's dramatic topography lie in its past, marked by internal processes and possibly cryovolcanic activity. As Charon cooled and compressed over millions of years, its crust split, resulting in vast canyons. At the same time, mountains may have formed from tectonic activity as the moon's surface flexed and broke, pushing some areas upward and raising peaks.
The interaction between Pluto and Charon is a kind of gravitational ballet in which both bodies are locked in a synchronized orbit. This means that Charon always faces Pluto on the same side, and vice versa, a phenomenon known as tidal locking. Unlike most moons, which orbit around their planets, Pluto and Charon orbit around a point in the space between them, known as the barycenter. This unique arrangement challenges the conventional definitions of planets and moons, suggesting a binary system where both bodies are partners in their celestial tandem. This gravitational partnership extends beyond Pluto and Charon, affecting the orbits of Pluto's smaller moons, Styx, Nix, Gibberos, and Hydra. Charon's presence stabilizes these smaller satellites, maintaining the complex balance of the system. The dynamics of this mini-solar system give us valuable insight into the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kuiper Belt, Pluto stands like a sentinel at the edge of our solar system. This region, a vast cluster of icy bodies extending beyond the orbit of Neptune, is a relic of the early solar system and holds the keys to understanding the formation and evolution of our cosmic neighbor. Pluto, once thought to be the 9th planet, has found its relatives among the vast number of Kuiper Belt objects, or KBOS. Like dwarf planets like Haumea and Makemake, to smaller, lesser-known bodies, each KBO has its own story that contributes to the picture of the solar system. Pluto's varied landscape, from nitrogen ice plains to towering mountains and dynamic atmospheres, reflect the complexity and diversity of the Kuiper Belt landscape. The Kuiper Belt is a window to the past, a frozen archive of the birth of the solar system. The objects included in it, including Pluto,
are remnants of the time of planetary formation, untouched by the sun's heat. Their composition, ice mixed with rocks, gives an idea of the materials that abounded in the early solar system and allows us to understand the processes that led to the birth of the planets. Exploring Pluto and its neighbors in the Kuiper Belt has far-reaching implications for our understanding of the solar system. Each mission, like the New Horizons flyby of Pluto and Arrokoth, peels away layers of mystery, revealing the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to consider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluto's position in the Kuiper Belt emphasizes the interconnectedness of celestial bodies, from the smallest piece of ice to the largest gas giant.
The dynamics of the Kuiper Belt, with its resonances and orbital interactions, influence the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting the environment of Neptune. However, New Horizons exploration didn't end there. After its historic flyby of Pluto, it traveled onward to Arrokoth, a Kuiper Belt object, meeting it on January 1, 2019, marking the next milestone in space exploration. Arrokoth, resembling a clay snowman, demonstrated the soft merger of two primordial objects, offering unprecedented insight into the building blocks of the early solar system. The story of Arrokoth's formation is a testament to the slow and gentle processes that dominated the outer regions of the early solar system. The large lobe, called Wennu, is not a single formation but a cluster of a dozen rocks, each more than 3 miles wide, huddled around a central slab. This cluster refutes previous notions of high-velocity collisions in planetary formation, suggesting instead a gradual merger at speeds of less than a dozen feet per second. This intricate interaction between two lobes, losing angular momentum and smoothly merging, forms an image of a patient cosmos where the building blocks of the planets come together in a heavenly cycle of gravity and time. Looking ahead, the horizon of solar system exploration is littered with potential. Concepts for the next New Horizons missions are already stirring the imagination of scientists and engineers. One of them envisions an orbiter capable of mapping Pluto's surface with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by Pluto's axial tilt. The project, inspired by the legacy of Cassini, proposes to use Charon's gravity to create complex orbital trajectories around Pluto, allowing for a comprehensive study of the dwarf planet and its satellites. Such missions could utilize electric propulsion, replicating the success of NASA's Dawn, and could potentially go beyond the Pluto system and explore new frontiers in the Kuiper Belt. New technology, such as direct fusion drives, promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report titled "The Fusion-Enabled Pluto Orbiter and Lander" from NASA's Innovative Advanced Concepts (NIAC) program describes a mission to Pluto with a direct fusion drive. Using a fusion reactor, a 1,000-kilogram orbiter and landing module could reach Pluto in just 4 years, more than twice the speed of New Horizons. These promising propulsion systems could significantly shorten the travel time, opening new pages in the exploration of the distant worlds of our outskirts. As we travel the vastness of space, exploring distant worlds and discovering the secrets they hold, our understanding of the cosmos continues to evolve. The story of Pluto, from its discovery to the present day, is a vivid reminder of the dynamic nature of science and our attempts to categorize the universe around us. Pluto's unique orbital interaction with Neptune adds another layer to its fascinating story. During its 248-year orbit around the Sun, Pluto appears closer to the Sun than Neptune for a brief time, challenging the view of its position as the 9th planet. This crossing of orbits, when Pluto and Neptune change places, occurs because of the elliptical trajectory of Pluto's orbit and its inclination relative to the plane of the solar system. Despite this temporal shift, Pluto's overall trajectory ensures that there's no risk of collision with Neptune due to their mutual orbital resonance. The rather lengthy debate over Pluto's planetary status
has long sparked discussion and controversy that reaches far beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of planet in our solar system, which led to Pluto's reclassification as a dwarf planet. This moment was not only a turning point for Pluto, but also a catalyst for the reclassification of celestial bodies. Pluto's history is closely tied to the Kuiper Belt, a region teeming with objects that blur the boundaries between planets, moons, and smaller celestial bodies.
Studying Pluto and its neighbors makes us think about the wide range of characteristics that celestial bodies can possess, from their atmospheres and geology to their orbits and interactions. In the grand canvas of the cosmos, every thread, from the smallest asteroid to the mightiest gas giant, plays a critical role in the history of our solar system. As we stand at the threshold of new exploration, Pluto's legacy and the knowledge gained from the Kuiper Belt serve as beacons guiding us to a deeper understanding of our place in the universe. Rethinking our cosmic neighborhood is not just about the labels we place on it, but about embracing the diversity and complexity of the universe. Saturn has captivated the human imagination. From ancient civilizations to modern astronomers, the Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. How? The mystery deepens. Saturn has long been a symbol of the unknown and mysterious. Its iconic rings have been the subject of wonder and speculation since the time of Galileo. But what if we told you that these rings, however eternal they may seem, are actually a fleeting cosmic phenomenon? Adding to the intrigue is a storm twice the width of Earth, with a mysterious hexagonal shape that's raging at Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries don't end there. Saturn's satellites, Titan and Enceladus, offer conditions that could potentially support life. Lakes of liquid methane and geysers spewing water and organic material into space make these satellites more than just celestial bodies. They're potential homes for life. Join us for a closer look at this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who first pointed his telescope at Saturn in 1610. What he saw puzzled him, a planet with something like ears. He didn't realize he was looking at the edges of Saturn's magnificent rings, a feature that would puzzle astronomers for centuries to come. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 that Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. Moving into the modern era, we witnessed the Pioneer 11 mission, the first spacecraft to fly past Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were once inaccessible to Earth's telescopes and us. But it was the Cassini mission that truly revealed Saturn in all its glory. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings, and its satellites. From discovering plumes of water ice on Enceladus to capturing the ethereal beauty of a hexagonal-shaped storm at Saturn's North Pole, Cassini revolutionized our understanding of this distant world. And here's an interesting point. Long before the advent of telescopes, the Maori people of New Zealand had myths that described Saturn as having a peri-arrow, or belt, around it. How they knew this remains a matter of debate and speculation. But as we'll see later, Saturn holds more than one mystery. What do you think could have created a hexagonal storm with an area larger than the Earth itself? Saturn harbors a geometric enigma at its North Pole, a six-sided storm that's puzzled scientists for decades. This six-sided wonder is not just a superficial feature, but a deep and enduring mystery that breaks down the understanding of fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft. But it wasn't until the Cassini mission, which orbited Saturn from 2004 to 2017, that we got a front-row seat to this cosmic spectacle. Cassini's high-resolution images showed a symmetrical jet stream surrounding the hurricane-like vortex at the center of the hexagon. Unlike Earth's chaotic weather systems, Saturn's hexagon is a masterpiece of geometric precision. So what's causing this hexagonal storm? Researchers at Harvard University have developed a 3D model that suggests deep thermal convection in Saturn's outer layers may be the culprit. This model shows that the storm could spread thousands of kilometers deep into Saturn's atmosphere, well beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in a laboratory setting. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they provide a glimpse of extraterrestrial phenomena. Saturn's hexagonal vortex contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of the gas giants from the Earth group planets. The longevity of the hexagon is another mystery.
It's been observed for at least 4 decades, and possibly much longer. This steady feature suggests that everything that feeds the hexagon is not a temporary phenomenon, but a stable, perhaps even permanent, aspect of Saturn's internal dynamics. Let's shift our attention from the mystery of the hexagon to another wonder of Saturn. Saturn's rings are more than just celestial jewelry. They're dynamic, ever-changing systems that interest astronomers and the public alike. But what are these rings made of, and why are they so short-lived? Saturn's rings are composed mostly of water ice, with a mixture of dust and rocky material. They range in size from tiny particles to huge chunks the size of houses. These ice particles are not static. They're in constant motion under the influence of Saturn's gravity and the gravitational pull of its satellites. The rings are divided into several subdivisions and gaps, each with its own unique characteristics. Most notable are the A, B, and C rings, separated by gaps such as the Cassini ring, a gap 3,000 miles between the A and B rings. The origin of Saturn's rings has been the subject of debate. One popular theory suggests that they formed from the remnants of a shattered moon. Another theory states that they're the remnants of material from the formation of the solar system captured by Saturn's gravitational pull. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on the rate of dust contamination. Saturn's rings don't last forever. They're slowly disappearing because of a phenomenon known as ring rain, in which ring particles are drawn into Saturn's atmosphere. This process is accelerated by micrometeoroid bombardment and interaction with Saturn's magnetic field.
At the current rate, some scientists predict that Saturn's rings could disappear within 100 million years. The depletion of the rings would not only change Saturn's appearance, but could also have consequences for its atmosphere and magnetic field. As we pause for a moment, we realize that even the most fascinating features of our universe are not immune to the inexorable forces of physics, doomed to disappear into the chronicle of eternity. Saturn, the ringed giant of our solar system, is not just a celestial wonder. It's also a cosmic playground that contains some of the most intriguing satellites. 2 of which, Titan and Enceladus, have fascinated scientists and sparked debate about the potential for life beyond Earth. Titan, Saturn's largest satellite, is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what's truly amazing is Titan's rate of removal from Saturn, 100 times faster than previously thought, amounting to a staggering 4.3 inches per year. This rapid drift suggests a dynamic and evolving relationship between Titan and Saturn. Could this drift affect Titan's internal dynamics, and perhaps even its potential for the existence of life? An atmosphere rich in organic compounds such as nitrogen and methane, and the possibility of an underground ocean, make Titan a tempting target for the search for extraterrestrial life. But the question remains, what would life look like in an environment so radically different from Earth's? And let's remember Enceladus, another satellite of Saturn that's very different from Titan. It's an icy world with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the concept of an ocean world to a new level. Not only does it have a subsurface ocean, but it also sprays it into space, where samples of it can be collected by a space probe. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water erupting from hydrothermal vents. Hydrothermal vents can provide the necessary conditions for life as we know it. On Earth, these vents are teeming with life forms that thrive in extreme conditions. Could Enceladus's vents be home to similar but alien life forms? Enceladus also contributes to Saturn's E-ring, a unique characteristic that further enriches the dynamic relationship between the Moon and its host planet. The icy particles in this ring open a window into the Moon's internal chemistry, providing clues that may reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but quite different in their characteristics. Both present compelling arguments in favor of the potential for life, fueling our curiosity. As we ponder the possibilities of life on Saturn's satellites, it's worth noting that our curiosity is not limited to telescopes and computer modeling.
Upcoming missions aim to study these satellites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan. Scheduled for launch in the 2030s, this rotorcraft will fly over Titan's diverse terrain, from dunes to impact craters. Dragonfly's main goal is to search for the building blocks of life. It will analyze complex organic compounds in the atmosphere and on the surface, providing invaluable data on Titan's chemistry. Equipped with a suite of scientific instruments, Dragonfly seeks to understand the geologic processes on the Moon and how they relate to its potential for life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although no missions to Enceladus are currently planned, the Moon's potential for life has made it a prime candidate for future exploration. Scientists are proposing missions that could fly through Enceladus's plumes and directly sample its underground ocean. Such a mission could analyze the chemistry of the plumes in search of signs of life or prebiotic chemistry. The presence of hydrothermal vents in Enceladus's oceans adds another layer of intrigue, suggesting an environment in which life could potentially thrive. Despite the technical challenges, a mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence for the existence of extraterrestrial life, or at least provide clues to the conditions necessary for life to exist. As we mentioned, Saturn's rings don't last forever, as we once thought. Recent studies have shown that a process that can last hundreds of millions of years is causing these icy wonders to slowly fade away. But what significance does this have for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, composed mostly of water, causes a decrease in electron density in Saturn's atmosphere. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. Ring rain is not just a trickle, it's a stream that carries away water in amounts equivalent to an Olympic-sized swimming pool every half hour. Compounding the mystery is the relative youth of Saturn's rings. Although Saturn itself is about 4.6 billion years old, data from NASA's Cassini mission suggests that the rings may be only a few hundred million years old. This leads us to wonder, if Saturn's rings are so young, what catastrophic event could have led to their formation? Was it the destruction of a moon? Or perhaps the capture of a passing comet? Cassini's space dust analyzer has added another layer of complexity.
Over 13 years, it's collected 163 dust particles that came from outside the Saturn system. Surprisingly, the rings turned out to be quite clean, suggesting that they hadn't existed long enough to accumulate excess cosmic dust. This cleanliness raises the question, if the rings are young, why haven't they collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age and their interaction with the wider cosmic environment. It's as if the rings are in a cosmic laboratory room, or clean room, isolated from the dust that permeates the rest of the solar system. As the rings are depleted, Saturn's appearance will undergo a dramatic transformation. These rings have been the planet's hallmark. Their disappearance would not only change Saturn's appearance, but could also have unknown consequences for its atmosphere,
perhaps even affecting the planet's albedo and heat retention. The loss of the rings could have a cascading effect on Saturn's atmosphere, potentially altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making them a subject of intense scientific interest. Interestingly, the fate of Saturn's rings may be inextricably linked to its satellites. Some theories suggest that gravitational instability may have destroyed some of the icy satellites orbiting Saturn, providing enough material to form the rings. Saturn's rings and satellites are like partners in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can say, unequivocally, that the fate of one can shed light on the mysteries of the other.